supposed to be doing when it's supposed to be doing the shape?
Well, if we don't let them go through it, we're
Weird,
never
wouldn't
going to
you
know.
How intricate could you get when you're not doing the right thing? Probably not too
We
intricate.
don't know because we're not letting them go through it. So we got to
You
give them
don't
some
know.
breathing room to go over
You
it.
think it's doing a circle shape? I know it's not. So if you don't know, I don't know what to tell you.
Oh,
So, so you're using this total station, and what kind of a camera do you have hooked to that?
Oh, it's just my cell phone. It's a Samsung S9 Galaxy, I think.
I see.
Running Android.
I see. And then now total station, what is like the distance of proper usage? Like, can you go? Do you use that commercially to look out miles and miles? Is that more of a close, like for like surveying that they do, maybe 200 yards or something like that?
So they simply measure angles. The difference between a theodolite and a total station is that a theodolite just measures angles. A theodolite or a total station also has an optical rangefinder on it, like a laser rangefinder, and it can bounce a light pulse off of a reflector in the distance and then measure the time it takes the light to come back, and so it knows the distance, and so that's why it's called a total station, because it measures the two angles and the distance, and then from that it can internally create XYZ coordinates out of those two angles and the distance. So the distance that laser can reach out has a limitation because it's only so bright. It has to be eye safe. It can't. It's designed to be unable to damage anyone's eyes if you shoot it at somebody, because you're literally pointing it at your rod man out there. So the distance on the rangefinders have specified limits because just beyond that, not enough light comes back for it to measure. There's no limit on the distance that you can measure an angle at. It just measures an angle. So in a lot of uses is just for short distances because that's all they got to do. But when they need to do long distances with them, they do it. And back before GPS surveying was, what everybody used anyway, they did long shots with theodolites all the time. But now it's a lot easier just to get a surveying GPS type system, and it just gives you your position without having to even shoot to any reference points, really.
Okay, I see. So when you're using that total station, from what I'm gathering, what you're saying, that looking at like those boats that were going over the sign, or those two large ships that were those ships anchored, or were they moving?
They were moving.
They were the two big ones.
Yes.
Okay, so I guess you could say that were those wasn't giving us distance measurements to those, was it? You were relying on Google Maps for that, weren't you?
Yes. I used the total station to get the distance measurement to the sign because that was a reflective sign and I could bounce my light signal off that. The ships, of course, there was no reflector on them, so there was no way the total station could measure the distance to those, so I was simply measuring angle or just, providing the visual view. But I used an AIS receiver to receive the real-time positions from the ships, and I recorded that, and then I put that into Google Maps or Google Earth and then measured the distances that way.
Okay, cool. So, when you're measuring angles like that, is that subject to refraction too?
Oh, absolutely. Because the instrument simply measures the angle of the light as it enters the lens of the device. What happens to it before it enters the lens is, the instrument doesn't know about that. It just measures the angle that the light hits the lens at.
Right, just like any
Oh, what do you
other,
know?
Right.
just like any other camera would, or anything like that. Our eyes doing the same thing. Our eyes, basically.
Exactly.
Okay.
Look at that.
So,
Their Democ is muted. Who would have guessed?
so, so, um,
Ooh, barrel riding.
how you doing?
Sorry.
Ever ride any barrels?
I have attempted to walk on some barrels in the water.
Anyway, getting back to this total station, um, those observations you made. So the one with the ships, those two big ships, I guess those were actually two different photos. I think you said that one of them was 29 degrees. The water line was 29 degrees. Is it degrees above the total station?
It wouldn't have been degrees. Let me pop it up here. It might have been arc minutes you're thinking of. But hold on, I'll post the picture and I'll pop it up so I can see.
You the man.
Seconds. Man.
Okay. So on the hot calm day with what I'm saying is high refraction, the water line on the ship was 2 arc minutes and 36 arc seconds above eye level. And then on the cooler, blustery day, it was 1 arc minute and 51 arc seconds below eye level.
So using those angles, are you able to calculate how many feet that would translate into?
Absolutely. Hold on. I'm just going to convert those to degrees and then I'll get those numbers for you. Okay, that looks like a 0.041 degree difference. And the distance is 7 miles. Oh, actually I subtracted instead of added. Okay, 0.46 degrees of angle difference.
You're figuring out the feet now?
Yes. $29.5 feet.
The other one was less than that, wasn't it? It was like 21 or 19 feet or something like that. I think you told me, or something like that.
Maybe I don't remember what I told you exactly or what we were talking about. Maybe I had only calculated for the height above eye level. I bet that's what I did. Let me try putting that angle in by itself.
Yeah, I think that's the one I'm looking for.
Okay, the height above eye level was 28 feet.
That's at the water line.
Yes, the water line of the ship, where the water laps against the side of the hull.
And then the auto level is how high above the water level that those water lines are at?
The total station was a few feet above the water. I don't remember exactly. Let me see if I can find that out.
Like 3 or 4 feet.
Yeah. So yes, something
Yeah,
like that.
if you said 4 feet, and then how using a Earth curve calculator, how far would that 4 feet? How far would the geometric horizon be? Sorry, I'm making you do all this, but I'd probably
No,
stumble through it.
that's okay. Without any refraction, the horizon would be at 2.45 miles, and there would be 13.8 hidden feet off the bottom of the ship, with a 4-foot observer height at a distance of 7 miles.
So it's exactly the opposite of what you would expect using that Earth curve calculator, or am I getting something wrong there?
Oh no, it's raised up much more than just opposite. It, instead of, if it was just opposite, it would have about 14 feet of rise instead of 14 feet of hidden, but it's got like 29 feet of rise.
Right, right. So using the geometric horizons, part of the water line would be hidden, huh? I mean, the water line would be hidden and part of the boat would be hidden, but instead, it's all visible. And yeah, it's really weird, huh?
Well, it looks like refraction to me. I was able to replicate it in my fish tank using density gradients, and we know the ship's not that high above the observer.
Yeah, I totally agree, with the fact that it's definitely lifted up. And I mean, I don't know what else you could account. It doesn't fit any perspective, that doesn't fit what perspective would say that you should be seeing. Isn't that true?
That is true.
So, and the only other thing that you might think that would cause, that much discrepancy is, the lenses in both the total station and the cell phone that you're hooking the total station to.
Well, the crosshairs are integral to the light path in the total station, so they the cell phone really can't mess with that.
I just mean the lenses. People say that it's aberration and all that. I meant that the only other thing in that whole, your whole setup could cause any kind of variation would be like, lens diffraction or, refract. What is it called? Diffraction, or you know what I mean?
I'm not sure Uh, I'm not sure you understand what those words mean. No offense.
Well, I just mean like, you know how they say that at the edges of pictures, there's a certain amount of distortion,
Oh yeah, like pin cushion or barrel distortion.
right? And then there's also the you know lights focusing at different spots.
Oh, the
They call
chromatic
that,
aberration. Yeah,
right?
but
That kind of,
right, these are corrected lenses, and the way that the theodolite and total station are designed, the actual measuring is always done in exactly the center of the lenses and the whole everything. That's why the crosshairs is crosses right in the very center, where all those distortions are very minimal and very controlled. So it really doesn't affect the reading.
yeah, I totally understand what you're saying, but I mean all lenses are none are perfect. They're going to have a little bit. I'm not like calling into question, you know, whether this thing is capable of doing the job. What I'm just saying is that that's the only sort of variable in the whole thing. You've got nothing else you can attribute to this. The reason that those water lines are so far above the, you know, so far above where they should be. Um, that's the only thing I can think of that would mess up this whole thing is some kind of, you know, your cell phone has a little lens in it. Our eyes have little lenses in them, and that's the only other thing I can imagine that would have any effect on those pictures other than refraction. What else would it be?
No, that's about it. And the lens argument really doesn't even make sense once you understand how lenses work.
What?
Because the focal point of those lenses is a physical property of their geometry, basically, and the whole thing is constructed out of rigid materials, and the crosshairs are very, very rigidly fixed in place, and it's all lined up, so it really can't not work as it's intended. Does that make sense?
Yeah, I think it's working as it's intended, but I'm just trying to, you know, look at this more like an experiment. What other factors could be having an effect? And like I think you're right that you know those lenses in the both the our eyes and in that the camera that you're using, the cell phone and the theodolite are plenty you know efficient to do what you're doing with it right there. That's what it would seem like to me.
Yeah, and that's why I set up the other one with the sign, because whatever one might suspect with is going on with the lenses, if you put a physical obstruction between you and the target and you can still see the target, you pretty much know the light is somehow bending over the obstruction.
Yeah, yeah. Another question I had was now you said that one of the pictures is of a warm day with not much wind. Which one was that? Did it have more of the was it the boat higher in that picture, or was it the windy day where the boat was higher?
It's on the warm, calm days that raise things up.
Right, and that would make so much sense because you know that water in the strait there is probably no more than 52 degrees, I would imagine.
Yeah, it doesn't get very warm because
Yeah,
it drains out as the tide changes every um, 12 hours or whatever, and then comes flushing back in. So there's a kind of a constant interchange with the ocean.
yeah, I've surfed up there, and I live the Columbia River, and when I used to go up there to surf, it would always be the water would always be quite a few degrees cooler than the Columbia River.
Yeah, so you know what it's like. It's no Baja.
Right, and then you said it was a warm day and not much wind, and it can get in the 80s there in the summer, huh?
Oh yeah,
So that's a perfect setup for a lot of refraction.
exactly.
Yeah, yeah, you know, and okay, so when you know when you have a discussion about the horizon rising to eye level, and people point, I guess, total stations at the horizon or something close to the horizon, and they see that it's the horizon's actually below below eye level. Isn't that the case more times than not?
Yes. In order to get this horizon above the eye level stuff, you got to get down close to the water. When you actually start getting up 20, 30, 40 feet, then it's pretty much never going to happen in this climate. Maybe it happens in California, but if you get up a couple hundred feet, it's basically never going to happen.
It's never going to rise to eye level. That's what you're saying.
Right.
So, kind of, these pictures here are totally destroying that idea that the horizon rise to eye level. It rises way above the eye level sometimes.
Yes, if you're down by the water, if the weather's correct.
Right, so with a lot of refraction, the horizon actually rises way above eye level. That I never considered that. You know, that's sort of an argument against the black swan in a way. Although the horizon really isn't, you know, an actual thing. It's just it's just a visual perception of this the sky meeting the ground or water.
Right, but it does raise some questions about, could the black swan scenes also work on a globe if the light can curve like that?
Well, it would be nice to know whether the horizon in the black swan picture is above, below, or at eye level. Does anyone know that?
I would love to know that, but I don't know that.
Because that's kind of like the same kind of conditions. You've got the channel, Santa Barbara Channel, the water's probably no more than 50, maybe 60 degrees on a summer day. It's cold in that channel.
Oh, it's
And
got a
then-
lot of interchange with the ocean too, doesn't it?
Yeah, and then you've got there's no wind that day, and I mean I used to live in Southern California. There's a lot of warm, sunny days, So that's a really great. The black swan situation is a really great setup for just what we're seeing in these boat pictures that you have. That the horizon might have been way above eye level. In the video, I remember, I think it was the black swan that, the most popular black swan picture where, isn't there a guy on a stand-up paddleboard in the foreground?
I think I remember seeing that. Yeah, I don't remember which one or where it is, but I do believe I saw that.
I wonder if that guy is above. He would kind of be like the representation of the sign you had in your pictures.
Right. If we knew his distance and his height and the observer height, that would be interesting.
And if you could have had a total station that, like you have, that would have measured that angle, and therefore you could have seen if it was above eye level or not. That would have been an interesting thing too.
Yeah, definitely. I wonder if we could get Jay Tolan to go try this out. He's in California, and he's got a theodolite.
To be off topic here, you might try that Mountain Dew. The new Mountain Dew flavor.
Never mind that.
Who is that cowboy?
I don't know.
Anyway, it kind of, and I've been thinking about that. I had that all, in my mind already. I just wanted to verify that with you, that idea that the horizon can be way higher than eye level. So in pictures like the black swan, the more I look at these long distance things, it just makes it's more suspect. There is no way to tell really what the hell we're looking at. Things are getting bent, lights getting bent and warped all over the place. How can we make any definitive claims one way or another?
Well, the best thing I can think of is to find a technique that doesn't yield wildly varying results, you know?
Well, just the fact that there are wildly varying results is enough to me, for me to think that we can't rely on optical things very much to tell us what the shape of the Earth is.
Well, if you're down near the water or your line of sight is passing near the water, then I agree completely. If your line of sight passes near the water and it's not a really blustery, cold, windy day where the air is just totally mixed up and homogeneous, then yeah, all bets are off. But what I've found is if your line of sight is at least a couple hundred feet above sea level, and then mostly, up over 1,000 feet for most of its journey, like to a mountaintop or something, then the consistency becomes pretty good.
So what you're saying is that things at that altitude, things that should be at eye level are, and things above it are, and things that are below your eye level are below eye level. Is that what you're saying?
Well, yes, plus 8 inches per mile squared of depth. But it's consistent. The point I'm making is that it's consistent. Whereas if you're near the water surface, it's completely inconsistent. It could appear below you, at eye level, above eye level, way above eye level. But when you get a couple hundred feet up, then the angles become much more reliable.
And they always show that that the horizon is you can see the geometric horizon when you're at that height. Then, what you're saying?
Well, no, you don't need it. If you have a total station or a theodolite, you don't need a horizon to reference to. You can just measure the angle to like a mountain peak or something.
And you're saying that the mountain peak will exactly match some kind of calculation that you make, that using numbers that total station will measure an angle that matches up with your calculation of where that mountaintop should be.
Yes, on a globe.
And it's always reliable.
Well, much more reliable. So, by way of example, I took like 20 some odd shots at a certain mountain that I can see from my yard that's 75 miles away, and I started in like 2019. I skipped a year, and then I did it in, I think, 2021, 2022, and then of course I in 2023. And I did it at all different times of year and all different times of day. And I kept all the, whatever outliers or inaccurate readings I got that, might have been due to weather conditions or whatever. I kept them all. I put them all in a spreadsheet. And the average missing height was 3,200 feet. The range of my measurements were all within a plus or minus 100-foot range. Does that make sense?
I see what you're saying, yeah.
So I've got a plus or minus uncertainty of 100 feet. But
so the outliers were 100 feet.
Well, they weren't there. I didn't actually really need get very many real outliers. Let me get you the chart.
You have an average. Real quick. He's got an average position, an apparent position. He's got an average apparent position of within 100 feet. Not once did he get an actual position.
Right. I took 29 measurements and averaged them, and calculated the minimum and the maximum.
No. I'm saying every time you went out and measured, you got an apparent position. So you have an average apparent position, never the actual position.
Oh, yes. All optical angle measurements are apparent. Always.
Apparent meaning not actual.
Well, you're measuring the angle of you're measuring the actual angle of the light as it arrives.
The actual angle to the apparent position.
Yeah.
Okay, so not once did you get an actual position, Just because you have a good average of an apparent position doesn't mean that was ever the actual position.
That's a good argument, Jeremy. But what I wanted to know too was when you say you looked at this mountain from your backyard or wherever that is, what's the altitude or the elevation of your yard where you're looking at that from?
180 feet or whatever, something like that.
Do you ever go up higher and do that, and then see if you're you get even more accurate apparent positions?
Oh yes, I've done them from different heights, but I've only done 29 shots to the same location from the same location of this particular shot because of the convenience of doing it from my backyard. But I also did, let's see how many these are. 26 shots, some of which aren't mine, but most of them are, of different heights where the observer height was as low as 4 feet and as high as 8,934 feet, and the target height was as low as 4 feet and as high as 14,179 feet. And also at different distances.
Can you hear me?
Now I do, but for a while I didn't.
Yeah, I got bounced out for a minute. But okay, so what you said, what was that one you said about the other one where you did a bunch of shots? I didn't hear that.
Yeah, I did most of 26 shots. A few of them are from other people, as notated in the link I just posted for you. But they were at heights from observer heights from 4 feet to 8,934 feet, with target heights from 4 feet to 14,179 feet, and distances from 1.5 miles to 105 miles.
I see.
Oh, and this includes data from 4 states in the United States and 3 countries: the United States, the UK, and Australia.
Ah. So
Tons and tons of apparent positions they got all over the place. Almost an unlimited amount of apparent positions, not actual.
Right, but it's kind of the best thing that I can personally figure out what to do myself, and I'm certainly open to suggestions for something better. But it is interesting that even these apparent positions match the globe model so closely.
They don't, not really. How about the one you guys were just going over when they were supposed to be 14 feet hidden, but it was 28 feet higher? Aren't those the number you just threw out at us like 10 minutes ago?
yeah, that was the one where it was down right on the water, Jeremy, on a real refraction day. Yeah, that's what we were saying, that close to the water like that or down by the surface, you're going to get all this refraction, like, which is pretty much demonstrated by those shots that he did with his total station. And then he says he goes up higher, and his apparent average apparent his averages of all the apparent positions he shoots kind of go with what the
Yeah, it
globe.
probably tightens up. There's less atmospheric effects. It's still higher or lower sometimes within, would you say, 100 feet?
Yeah, it's 75 miles. I found it to be plus or minus 100 feet out of 29 readings.
Of your average apparent position.
Yes.
Yeah. So which one matched the globe?
I'm not sure I understand the question.
How many measurements did you take?
29.
Okay, which one of them matched the globe?
I'm not sure what you mean by matched. They
One
were all.
of them matched the globe. Well, I mean, some of them matched the globe. Obviously, if it was within 100 feet, some of them didn't match the globe, right?
Well, they all. without any compensation for atmospheric refraction, they were all about 7 inches per mile squared of depth, of missing height.
Even the one that was at the bottom of the spectrum and at the top of the spectrum?
Yeah, they were about 7 inches per mile squared of missing height.
How could that be if they were one of them was 100 feet off the other one?
Well, that's why I say about. Approximately.
Yes. So one of them definitely didn't. I mean, the one at the bottom definitely. The one at the bottom and the one at the top couldn't have matched the globe, obviously, right?
Not exactly. I mean, nothing matches anything exactly. There's always some margin of error.
And what would cause that margin of error?
It would have had to be atmospheric conditions.
So you're saying refraction.
Uh-huh.
And then you're using a total station, and you're saying that those are, really, really accurate. Even at what was the distance of these ones you shot, the mountain shots you did?
The one where I did 29 shots to the same mountain from the same place was 75 miles.
And what about the other one? What was that, like 100 or something?
The other one where I did a bunch of shots at different distances was one from 1.5 miles to 105 miles was the longest.
Oh, I see. So, now is the total I think I asked you this before, but is that total station, is that within its workable range?
Yes. It just measures an angle.
Right.
But it's up to the user to know what sort of margin of error they're going to get due to the atmospheric conditions. Well, which is the same case even at 50 yards. If you're trying to shoot over really hot on a hot day over cold water at 50 yards, you're still going to have an increased margin of error due to refraction. It's all about knowing what your limits are and working within those, which is what all of life's about.
Right, but I mean, have you ever heard anyone argue that the theodolite isn't supposed to be used? I mean, at the total station is not supposed to be used at that distance. It is not considered accurate and wouldn't be used professionally. I'm not saying that it is. I'm just saying, is there an argument for that?
I've heard that argument a lot from people who've never used them and want to discredit my results without actually explaining numerically why. But
is there a manual that comes with it that defines what that range, workable range is?
Oh yeah, the manuals always specify the specifications of the instrument itself. For example, plus or minus 4 arc seconds, or plus or minus 2 arc seconds, or whatever. But that's an angle, that's not a distance. Because that is their limitation of accuracy, is angle, in and of the instrument itself.
Right, so there's an inaccuracy in its ability to measure angles, huh?
Yes.
And am I not thinking about this right? But as you take an angle further and further out, the discrepancies get bigger and bigger, don't they?
Well,
distance, I mean. Distance. Right.
Right. So the linear height error becomes linearly greater with the distance just due to the geometry of it. The refraction effects also compound. But that's not a limitation of the instrument, that's just a limitation of our real world. And that's why the surveyors that did the great triangulations, they would literally, build towers 30, 40, 50, 60 feet high just to put the surveyors and the guy with the light up there so they could shoot from mountaintop to mountaintop. But they did long distances like that.
Uh-huh.
It's
right.
all. Go ahead.
And it sounds like a good method to do it, but you do have to consider that there's refraction even at those heights, and that the instrument gets less accurate with distance.
Well, the angle does
I'm
not.
not saying it. I'm not saying it's not a globe because of that. I'm just saying that those are facts, aren't they?
The angle does not get any more less accurate
I,
due to the distance.
I
But
thought you said that there was an arc second, you know,
so,
discrepancy.
well, an arc second is, let's say, if at a certain distance an arc second equates to 1 foot of vertical error, at twice that distance it'll equate to twice that vertical error.
Right. So like compared to like that sign that you have uh, now on the water there, as opposed to looking at those mountains from your backyard, you're going to see a huge amount of variation, aren't you? Comparatively.
Say that again.
Well, okay. So when you're looking at that sign you had in the straits there, and you're measuring the angle to that,
Uh-huh.
there's going to be some error in there because the machine has an error in it, huh? I mean, it has flaws. It's not perfect.
Right, that machine is rated at plus or minus 4 arc seconds.
Right, and the distances will get greater and greater. You know, the distances that'll show up because of that error will be greater and greater with distance. We already agreed on that. So what I'm saying is that it's refraction, and that the flaws in the machine are the only two variables that I can think of. Is that right?
Yes.
And you don't know of any other variables that might affect, something like that?
Not that I can think of. I mean, well, so there is claimed to be, by the globe model, very slight deviations in plumb. Like if you're near a big heavy mountain, and it can pull plumb off a little bit. So the you might level your total station might think it's level, but it might actually be pointing up or down a little bit, a few arc seconds. So that can add or subtract a few arc seconds of error too. And that's all mapped out, allegedly. I can post you the maps if you like.
I don't think it's really necessary. I'm just trying to grasp the whole thing, Uh, I'm taking your word on that, that's the way it is. Yeah, it's just interesting because I never really considered. I didn't think that when you were using a total station like that or anything, if you could, just using a camera where you had some kind of a bubble level on a camera and you aimed it at the horizon, that the horizon sometimes could be way higher than eye level.
Yeah, I never really thought about it either till trying it out. And I'm like, well, that's interesting.
Yeah, it just goes against the whole perspective thing, like we were talking about, a couple days ago or whatever, how, things that are right at eye level will stay at eye level, and then, you know, things above will stay above, and things below will never go above eye level. This totally just shatters that whole perspective thing because we're saying either flaws in the instrument or refraction.
Right.
Fascinating.
And I don't think it's flaws in the instrument in my case, because for the set of measurements where I measured 29 times from from my backyard to the same mountain peak, I used 11 different instruments, and they all came in so close. So I know it wasn't just a fluke instrument giving a bad reading.
Yeah, I understand what you're saying there too. I'm not trying to lay a bunch of blame and make an argument for that we can't use your data there because the instruments were flawed. I'm not saying anything like that. All I'm saying is that's just one thing that could affect the results of the test that you did.
No, they're totally good questions, and I appreciate you asking them. And I asked myself some very questions already. So no, they're good questions.
Yeah. Yeah, it's all a learning process. The more I look at stuff, especially when you're dealing with light, it seems like it's just another one of those things where got to cross a line of faith or something, and uh, you know, we don't know what's going on.
Right, and that's why I kind of started exploring the behavior of light in controlled environments with density gradients to kind of get an idea of what it was like.
Yeah, I started to get some really weird ideas. I was thinking about how people always say, in like in the flat Earth movement or whatever, people will say, "Oh, there's controlled opposition." A lot of these guys are just players, and I was thinking about QE, and how he brought this black swan in, uh, one day a couple years ago, that was going to crush the globe, and it did, it was this thing where he used these really refracted images. I'm not trying to say that he's not right. All I'm just saying is that I started to get all these paranoid thoughts like, oh, these guys, yeah, maybe they are controlled opposition. They're bringing in all these points to steer the argument in a certain direction. Um, you know what I mean? In order to hamper our attempt at really knowing what's going on. You know what I mean?
Right, right.
Yeah, I'm a real conspiracy guy in that way. I always think, why are people doing things? And it is really a fact of life that, when an enemy wants to control something, they control the opposition. If there's opposition, they try to infiltrate it and control it.
Yeah.
So here we went to from a completely sort of scientific discussion of optics, and I went into this complete tirade about controlled opposition and QE being an agent.
Where is QE these days?
I I used to listen to uh, Flat Earth Debate, and he used to be in there a lot. But I never listen to Flat Earth Debate anymore, so I don't know what he's up to. Is he still going into 24/7?
I'm sorry, say that again?
Is he still going into 24/7?
I don't know. I haven't seen him around in a while.
Yeah, I remember a few years ago he was talking about just getting into debating evolution and creation and all that.
How's my mic sound?
Not too bad. Did Jeremy ever catch up with you about them GPs? You
Yeah,
might.
if he's listening, tell him I'm working on it, but in a very yeah, I'm working on it. I had a very genius plan, but it's just going to take me a while.
Okay, so the
It's all
GPs
sorted
are
out.
in the mail.
Yeah, basically, yeah, that's right. Well, I'll tell you, you'll understand this. You'll understand this. You know what he's asking for, right?
No, I have no idea. I just keep hearing him saying, "Where's the Kosho with his GPs?"
He wants 4 stars, 4 GPs. First of all, I found 4 GPs where, just like kind of, I think you did this. I think you did something very similar to what I did, where you had 4 stars in like the 4 corners of the U.S. and showed how the diagonal doesn't match what it would be on a flat Earth, basically. You did something like that, didn't you?
Say that again.
You had 4 stars where 4 GPs on the 4 corners of the U.S.
Oh
You
yeah,
used the differences. You did something very similar to that, right? Have you shown that to Jeremy?
with the paper strips. I don't know.
Yeah, because he's asking for something very similar. But however, I'd also done that, and he then decided that to make it clear to the people he wants to share it with, he wants it to be a perfect square. So 4 stars, 4 celestial objects um, that would be used in celestial navigation, such that um, the 4 GPs or whatever would basically make a perfect square.
Oh,
Maybe on some kind of map.
right. That would make calculating the slack and the diagonals a lot easier, wouldn't it? You wouldn't have to cut out strips of paper like I did.
Yeah, yeah. Well, the other option though to what you did, because I was thinking about it, and there's no equation, there's no way to solve for the third side of a triangle if you have a scaling triangle. But there's just you can't do it with only 2 sides, and without any angles. However, if you have some kind of trapezoid, is it a trapezoid or whatever? I think it's called a trapezoid, right? Yeah. If you have some kind of trapezoid, which is a 4-sided object with any length sides, any angles, any lengths. If you have the sides of the trapezoid, then you can calculate what the angles are. And if you can calculate what the angles to the trapezoid are, you then have an angle to the triangle that you're going to use. So the two sides of the trapezoid, and you're trying to find the diagonal basically. So there's a way to do it, but I think based on the way I just shared that with you and the way I would share something like that, it's not. I'm not the best person at explaining things, and I think he needs something that you could present to a kindergartner or someone with less intelligence, really, and they would be able to, they wouldn't have that many. They would understand it, and so I think that's why he wants to square, because he wants to be able to present it without any question, like without having any confusion.
Right, because you can just take the square root of 2, and that, if the Earth is flat, that would be your diagonal length relative to your sides.
Exactly right. But still, however, I did find a way that actually, because I know you're familiar with the celestial navigation stars and all that in the almanac, and yeah. So at first, it would seem like that would be impossible, but actually, it's possible to find when that would occur if you allow yourself to use Saturn, Jupiter, Mars, and Venus as well, and possibly not having to use the moon. Using the sun makes it really hard because the sun's not going to be out at the same time as the stars. But yeah, so using those 4 planets, it's very possible that you can find a configuration where at some point in time there are 3 stars, or some combination of stars and planets that make a perfect square. So I'm just working on that right now. Maybe he's not listening, maybe he is, but it takes.
I think you're gonna take forever if you just look for that. I think you should write an algorithm to find it.
Well, Bacon,
Or did you just wake up, dude? Listen, man, I'm not. I don't know if I
wake up
said that.
midnight.
I'm just saying. I don't know if I said, but you said you did just wake up.
No. Who
Okay,
wakes up at
But
midnight?
regardless, Bacon. I'm not saying. I don't know if I said the words "look for." I'm talking about writing an algorithm. So that's what I'm doing. Yeah. I'm writing one.
How are you doing
that
it?
can look. Well, I have to. I'm going to feed in the PDFs for several almanacs and have it sparse out the data. And
There's an easier way.
oh yeah.
Yeah, you know, Prothet, he wrote an API that you can fetch the right ascension declination for any celestial, any of the stars in the almanac, or any planet, or the sun and the moon at any point in time. You can just send a request and it will answer you back with the right ascension declination.
Yeah, for any point in time. So you'll just have to send out a request for what's 5 million times 60, like 300 million requests for every year. You
Why?
want to for every object also.
No, you don't have to be like if you do that for stars, they won't change for a year basically. At least I mean across a year the position of the stars are not going to change, and I mean they will respect to the surface, but you don't need to request them for each point in time. You can request for one point in time, and you calculate from that. Planets, it's different story, but they change slowly. You don't need one like a request for each second. You can get a request for each like 12 hours, and you can interpolate between the positions, for example. So you don't have to keep making requests.
I agree
There
with
are
you.
plenty of ways
That
to
sounds like,
optimize it.
I agree with you. That sounds like another way to do it, but that even seems like it seems like they're both will require work that I'm gonna have to do anyways. Because I mean, this way with the almanacs and the PDFs, it's not that difficult. I just have to make sure I can parse the data from the PDF, and once I do that, I have all the data. So
if you want to already have like data of stars parsed.
Well, but what I'm saying is I'm gonna have a collection of all the data, so then I can make comparisons of okay, at what time do they overlap at this at this distance or whatever.
Mm-hmm.
You know what I mean? Because basically, I'd be looking for two stars that are either on the same. Yeah, it's actually difficult because even the square, this idea of a square, like
It makes
how does
it
even make sense?
unnecessarily difficult. I think it makes it unnecessarily difficult.
Yeah, I know, but that's Jeremy's fucking. Why am I even doing this? What am I doing this for this guy?
Yeah.
Why waste my
Sometimes I
time?
ask
But you know, what?
myself
I like challenges. You know how it is, dude.
yeah.
What was the name of the guy you were talking about?
If you have 4 points that are all equal distant and you have 4 GPs, then you can get the angles and the measurements and see whether the Earth is curving or planar.
If they're equidistant. Sorry,
go ahead, Bacon. Well, no. It's important to understand that a square and a rhombus, for example, neither of them have 4 equidistant points because I think as Bacon was about to say, and as he's shown me several times, a tetrahedron is the only shape that has 4 equidistant points. So the relationship you want with a square is that the sides are equidistant and the diagonals are
the same as each other.
Yeah, the same as each other, but they're like, yeah, exactly. So you don't have to be specific. Yeah, exactly. They're the same as each other.
Yeah,
1.4 times the size.
I think Jeremy once said, because that makes it more obvious that there's an accessing distance, so he can present it. But I mean, you can make it as obvious with any 4 points. You just do what Jesse did. You make a physical model of that, and that's it. It doesn't have to be square. Just any shape. If you want to check if it's coplanar or not, just print it and do what Jesse did. I think trying to make it a perfect square makes it unnecessarily difficult. Wouldn't you say so?
Hey, just tell me quick. Can you hear me? Can you hear me right now?
Yeah.
Okay. I'm not gonna be able to talk any longer. But yeah, you're right. It's unnecessarily difficult. I've already done it with the 4 sides of the trapezoid. Honestly, I listened to Nathan's show and listened to Jeremy's exchange with him, and this
Jeremy
whole
have been there?
thing is really for Jeremy than it is for them. They're past the point of no return, dude. Those guys, there's nothing that's gonna like the point that he's trying to make to them is already far more advanced than what they're gonna be able to deal with because they're still fixed. They're still fixed on the fact that you can't make an angular measurement, elevation angle measurement on a curved surface. So yeah, I'm gonna leave it there.
Right. Like George.
Yeah, well, exactly like George. It was
Yeah, you
George,
gotta
Tenth
have.
Man, Nathan.
You gotta have is four equal sides, all the whole perimeter. They all from dot to dot, from GP to GP. They all got to be the same length. Then you gotta have the diagonals symmetrical, meaning they have to both be the same length as each other. Once you got that shape, we're good. We're in business. We can get it going there.
Here's the problem. Okay, here's the fundamental problem with that.
No, but I want you to tell me here's the solution.
No, but no. The problem with what you requested is you weren't specific. Like you said that. So let's imagine we don't know what the shape of the Earth is, and we don't know anything about the surface, and you're asking to find something that exists like that exists where the 4 sides are the same and the 2 diagonals are the same. What if that can't be done?
Why? You have the sun and the moon to work with all year, bro. So you find 2
I know, but
stars.
what if the Earth is a sphere?
That would still happen on a sphere. That thing I just said would still happen on a sphere. That shape is
yeah.
It's extremely difficult to find.
It's not extremely difficult to find. Let me tell you what you do.
Oh, you say
no, but
that.
hold on. It's difficult to find, but it will happen on both models. What you're suggesting is not specific enough.
However, one of the models, it will happen on both models, but only one of the models will have the square root of 2 formula thingy in it. Yes, so here's what you do. You have all year with the sun and the moon. You don't have to get the distances at the same time. So you take 2 stars that are on one of the tropics, and then you just wait for the sun and the moon to get in the right position.
I know.
First of all, dude, this is easy peasy. Come on.
Yeah, I know. Listen, man, it's not. First of all, what you just said is not easy peasy, and that's already what I'm working on. Exactly what you just said. That's what I'm doing. I'm using the planets too. But it's not easy peasy, dude. Okay, and that's number 1. Yeah, it's not some over. It doesn't matter. But I'm gonna go because I don't want to keep. I'm the only reason I'm interjecting is because I'm about to go, and I just want to state this is God damn it. Oh no, but actually, Jeremy, you just changed the problem in a way that makes it surmountable. Because really, that's all you have to do. No, you're not one of the best.
Easy peasy lemon squeezy.
Oh my god, you're not one of the best, dude. You're the idea man. Okay, you're the guy who has ideas, and most of them are bad. Now, what was I? All right, the point is, what you just said though is exactly what you have to do. All you have to do is not worry about what shape the Earth is or what the difference is between the diagonals of the sides, but find 4 spots at a time where those 4 spots are equidistant on the sides and the 2 diagonals are equidistant. Once you have that, you confirm that you have a square-like structure, and if it were flat, it would definitely be a square. And the relationship between those diagonals and the sides is, like you said, 1.4, whatever, the square root of 2. Otherwise, it would be something fundamentally different. And so really all you have to do is confirm that you have some shape that it conforms to that conforms to the sides being equidistant and the diagonals being equidistant. That's fair enough.
Easy peasy.
Yeah, it is easy peasy, actually.
Lemon.
All right, fair enough. I'm going to be listening, but I'm going to be listening. I can't talk.
Jesse, are you still around?
Sure am.
So you said that when you took those all those photographs from your backyard of that mountain, and you got a you got about the outliers. You're saying the low outliers were what was it, 7 inches per mile squared rather than 8?
No, the average was 7 inches per mile squared with no correction applied for refraction at all.
Okay, I wonder what the difference in feet would be between the high outliers and the low outliers. We'll try to calculate that.
200 feet. Yeah, if the low outlier was minus 100 and the high outlier was plus 100, then the difference is 200.
And how high is the mountain?
Like 10,000 some, about 2 miles high. It's Mount Baker. You know Mount Baker.
Oh, okay.
You can probably see Mount Baker.
Not from where I live now, but I used to when I used to live up in the Puget Sound in Everett and up in Birch Bay for a while.
Oh, okay. If I apply standard atmospheric refraction correction to my measurement of the mountain 75 miles away, the measured missing height becomes 3,756 feet, which is, and the Earth curve calculator says it should be 3,750 feet. So my average is 6 feet off from the full globe model prediction. Maybe there was some snow on top. Do Jeremy's 4GPs need to be on any specific land masses, or can they just be anywhere?
I think anywhere will do. I mean that's. I think Jeremy should answer that, right? But
Do they have to be ones that are bright enough to see with the naked eye, or just anything that shows up in Stellarium?
No. He wants almanacs to, because I mean we're not going outside doing the measurements. We're going to trust the almanac because the almanac gives you the GP, and Celestial Navigation Math tells you what's the zenith angle you would read. And I think that's what Jeremy is going with. So we need the almanac.
Oh, so they have to be something listed in the almanac.
Mm-hmm. Yeah.
Okay.
So for planets, 59 stars, sun and moon. Hey, there, Jeremy. Now I'm wondering, how you're going to get the distances.
Well, all we need to do is get ones that have equal angles. In other words, GP1 has an equal angle to the star of GP2, and so on and so forth, all the way around the square, right?
Mm-hmm.
If they're each 10 degrees or 20 degrees or whatever, then that's all we need, right?
Mm-hmm. Yeah. And the diagonals must be the same, like
Right.
yeah. So you get a square shape, something square shape. I wrote an algorithm that would find 4 points as far as away from each other, in which you can make those measurements all in the same night. So I was basing my algorithm in where the sun is in the celestial sphere. So I would search in the other half, and I would search for stars. You can see the cities in which you can see the stars above the other cities, all in the same night. And the algorithm would take us some seconds to run. It was quite slow because my database had like 42,000 cities, and there is 59 stars. And I was only looking for stars, and that already took a while. What Jeremy wants, we have to, like, it's not gonna work to do. I mean, that's probably not gonna happen in one night. You're gonna have to combine night with different days and different periods of the year, because it's such a specific shape that it would be just too hard to find all that in one random night. So you're gonna have to check for a lot more data than just one night, and so you have to make a better algorithm. Otherwise, it's just gonna run forever. It has to be a smarter algorithm, a more efficient one. So I was trying to think about first finding the squares. So I get like all squares between those 42,000 cities, all 4 points that forms those squares, and then I will try to see if all those cities, which one of those have some celestial body on top of them, and if there's at least one group of 4 cities that all the cities are going to have celestial bodies overhead within some margin, because you have that's also a thing, you have to establish a margin, right? There's no, you're not going to find any instance in which all that matches perfectly. You're going to need some wiggle room, and the bigger the wiggle room, the sooner you find.
Right, and I think the defining boundary on that would be if it's close enough to square that both diagonals are unambiguously longer than they would be on a flat Earth, then that's probably close enough.
Can you say that again, sir?
Yeah, and I think if it's square enough so that both diagonals are unambiguously longer than they would be on a flat Earth, then that would probably be good enough, square enough.
Mm-hmm. Yeah.
It's just that if it's... Go ahead.
No, go ahead.
If it's so far out of square that one of the diagonals is not longer than the square root of 2, from one of the sides, then that's going to raise, questions.
Yeah. Okay, so look how like my algorithm found a very huge square. It's not a square. Like it doesn't have the same sides around the perimeter as Jeremy wants, but it's a huge square. And this can all come from the same night. I'll post on Livestream one text how big of a square the algorithm found. And that's just almanac stars.
Oh, well.
And all cities.
Maybe that's good enough. If both of those diagonals are larger than the smallest side times the square root of 2, then it can't fit on a flat Earth.
I think that's not enough. Like
Oh.
if you have a tiny side on the flat Earth, that would always happen. Right? Like if one of the sides is tiny, then the diagonals are always going to be bigger than the square root of 2 of that side.
Yeah, probably.
But yeah, I mean, we always have the option of asking you to do it for us and and doing it with real, like a physical
Just
model.
remember, my calipers are only 8 inches long.
Fair enough, yeah.
But, I mean, I could always do it in multiple steps to extend it on.
Yeah, that's true. No, but that's a calculation, not a measurement.
I guess it is at that. What are the zenith angles? What are your 6 zenith angles on that square
That's a good question, because I haven't checked if they exceed 90 degrees, which would mean the stars can even be seen by the other city.
Oh.
Let me check that. Yeah, they can't be too great, otherwise you can't see the star. I think I should limit them to 60 degrees of distance. So all stars are going to be above 30 degrees, which is when usually, like, no one corrects for refraction above 30 degrees. Some people don't correct above 15 degrees. But I think 30 is the highest line that I've seen people drawing from where you correct and when you don't correct. But let me get the lengths of the diagonals. Just give me a sec. There's a guy called Boom Boom BX Hick XK asking me to ask for him to be unmuted. So if there's any mod there, he's asking to be unmuted.
I think he got muted just a little while ago because he was drunk and just over talking.
Hey, Jesse, can you talk for a minute more?
Certainly.
Okay, so you said that the observation you made from your yard up to Mount Baker, you said that using standard refraction, you came very close to the globe model prediction of how high that mountain would be.
Yes, within 6 feet. Mine was
Within
6 feet high.
So
Which is
what you're doing.
no. Go ahead.
So what you're doing there is you're just taking it. When you say that, are you saying it's 7/6R?
Yes, that's standard atmospheric terrestrial refraction. I use 1 degree per 932 miles.
Okay, so that's an agreed upon average, huh?
Yes, that's what surveyors use. I mean, they use more complex, more accurate modeling, but that's a very good back of the napkin approximation. I found it highly consistent.
And you don't really know how much refraction there was in that particular situation, do you?
Correct. I only know which direction it's going. I don't know how much it is.
So you're just using what they've sort of, I guess, calculated or whatever. It's not. Yeah, you can't tell what the refraction is between you and Mount Baker on that day. You could maybe try to go and get all kinds of weather data, humidity, and all that, and try to maybe figure it out. But that would be pretty hard, wouldn't it?
Yes, you would basically need to fly a jet along the line of sight, measuring the temperature gradient. If I did that, then I would have had a much closer tolerance than plus or minus 100 feet.
So, no, wait, I didn't understand that last thing you said.
Well, I just measured, accepting whatever conditions there was, just measured, applied no corrections, and I got a range of plus to minus 100 feet. 3,200 feet missing, plus or minus, with a maximum deviation of 100 plus or minus 100 feet. If I had the ability to fly a jet along that 75-mile path with multiple temperature sensors to measure the actual air density gradient along that path, and then compensated for the gradient of that specific measurement time, then and applied that, then my readings would have been much closer to the average instead of deviating plus or minus 100 feet.
How do you know that?
Because people have put a lot of effort into calculating how much a temperature gradient causes something to appear raised up.
Right, but you're just arbitrarily saying that if you flew a plane and had all the temperature readings, that it would make it would make it even a better case for standard refraction or whatever the calculations are.
No, I was just saying it would allow me to have corrected my measurements to a result which was much tighter, with much less deviation from the average.
How do you know that when you don't have that? You don't have the data from the airplane. How can you say that?
Well, I'm not sure I understand your question. Maybe you're not understanding what I'm saying.
No, I think I know what you're saying. If you could fly in an airplane and take a temperature reading, humidity reading, whatever it is that's going to make refraction all along that way, say every mile or something, that's going to make it's going to make it more.
My phone down there.
It's going to make it closer to what you found. It's going to make it closer to 7/6R, isn't it? That's what you're saying, but you don't know what the data on the airplane would have been if that had been done.
And that's why my measurement deviated by plus or minus 100 feet. Because I have no idea what the air was like in that path of light.
Right, you have no idea. So to say that it would be one way or the other is, it would be wrong to assume that the airplane data, which you don't have had this.
Oops, he'll be back. He drops out some. He's using the web page interface for Discord, and it drops him out every so often. Hey, welcome back.
That's happened to me too.
Yeah, there's a lot of issues with the web version.
I got kicked out there, Jerry. Jesse, what was your response to what I said?
Carol, are you using the web version of Discord?
Yeah, I'm afraid I am.
Can you download the app? Because if you could, it tends to work a lot better if you download the actual Discord software and then install it.
Okay, I'll do that.
Yeah, it's just, I think it's just right on Discord's website. You can just download the actual software and then install it, and it tends to work a lot better.
Okay, great.
So no, it's not that bad of an assumption to say that if I knew the temperature density gradient along the path for each measurement, that I could correct for that temperature gradient, because we have formulas that actually allow us to plug in the degrees per meter of vertical temperature change, the rate of the gradient, and then it gives us the amount of curvature that light takes along that path.
Right, but you're acting like you already have that data out of the airplane to be able to do that, and you don't have that data. I understand what you're saying, and I agree with you that would be the most accurate way to do it, would be to fly an airplane and get these different weather readings or whatever, and then you could really hone in on it. It wouldn't be perfect because you could probably do it better if you put more, if you did more, if you did it every quarter mile rather than 1 mile, or what I'm saying. But none of us have that data unless you were to fly a plane in that from your backyard to the top of Mount Baker. You don't have that information, so you have to assume that it would be, it would match the globe model. I'm just trying to eliminate as many variables and figure out what's going on. I'm not really trying to argue with you or anything.
Sorry, I'm back. The neighbor kid.
Yeah, I'm just, either I'm not understanding something, but you're making the assumption that if you're flying an airplane and you're taking measurements of the temperature all along that way so you can calculate the refraction using that data, that you're going to come up with one that's a lot closer than the globe than you even got. But since you don't have that data from the airplane, you're assuming that the airplane would give you the data that would make it like that. It's just an assumption on your part, isn't it? Or am I missing something?
Well, no, we've done experiments and measurements, and we've quantified how the temperature gradient affects the apparent rising of things in the distance due to that gradient. So if we can measure the gradient, then we can literally predict how much it's going to be raised up, something in the distance will be raised up due to that gradient.
Right, but you can't measure that distance unless you have the plane and you go out and do it. I mean, you can't measure those temperatures and then plug them into your formulas to do that because you don't have them. So you don't know whether it would support the globe model or what it would do. You're just assuming.
Well, I wasn't even really saying it would support the globe model. I was just saying it would have reduced my margin of error.
Right, but it could have also made it hugely different.
How do you figure?
Well, I don't know. That's what I'm saying. We don't have the data from the airplane. And I'm sure the data from the airplane would, give us a more precise measurement, but since we don't have that data, we can't say one way or another which way that would go.
Okay. Well, I do actually hope to rig some temperature sensors up on my drone so I can, over shorter distances, measure the temperature gradient along the path of light, and then see how it does correlate. But I'll concede that I have not flown a plane 75 miles and measured the gradient. So does that help?
Yeah, it would be nice to see those, using a drone like that. Like you say, it would only be a shorter distances, but yeah. And am I being really pedantic about this, or am I raising a reasonable objection?
It's certainly reasonable from where you're coming from, and with your lack of experience with the physics of refraction and temperature gradients.
Well, I'm not, saying that I know anything about that. What I'm saying is that you're just assuming that the data from the airplane would do a certain thing, and we don't have the data from the airplane.
Well,
I'm not arguing the whole, science of refraction. I'm just saying that we could figure it out a lot closer if we had that data, but we don't know that data. I mean, there might be some variable in there, updraft, huge updrafts, between there and Mount Baker. I don't know, unicorns or leprechauns or whatever. I'm just saying that, it's a possibility that there could be something there that we're not able to see or calculate.
Well, there's always the possibility of the unknown, but that cuts both ways, right?
What?
There's always the possibility of the unknown, but that cuts both ways.
Yeah, that's exactly what I'm saying. We're completely clueless.
But what we do know is that a stable density gradient causes things to appear higher than they are, not lower. So while we don't know how much lower Mount Baker is than it appears, we know it is somewhat lower than it appears. We don't know how much, but we know it's not higher than it appears.
Right, but you're making another assumption there too. You're saying that certain density gradient would give you a certain refraction, and then you could calculate. And that's true. You don't know what that density gradient is between you and Mount Baker when you're taking those pictures.
But we do know that it's more dense at the lower elevation and less dense at the upper elevation, right? On average?
Yeah, I mean, down by the water, those pictures in Puget Sound, it's all screwed up.
And we know that even if there's no temperature gradient, there's still a pressure gradient, right? Because air pressure is greater at lower elevations.
Yes.
Okay, so we do know that the density gradient is bottom heavy along that line of sight to the top of the mountain. And we also know experimentally that a bottom heavy density gradient causes things to appear higher than they are, not lower, right?
Yeah, I totally agree with you there. The only thing I'm arguing, and I don't want to continue with this. I think we've pretty much made our points. Is that we don't know what the actual pressure, temperature, humidity, all those factors that can affect refraction are between you and Mount Baker. That's all I'm saying.
Right. But
So,
we know the limit to it.
no, we really don't. We don't know what's going on. I mean, unless you flew that plane, like you're saying, you don't really. You're just assuming that you know, or that you have a close idea of what's going on. But we can't say for sure. I mean, it's not very scientific to say that anyway, that there are things that might be influencing that you're not able to detect.
But I mean, that's kind of, I mean, let's say where things were different. Let's say I pointed my theodolite out, and every single time that mountain appeared at exactly the height that it should on a flat Earth. Let's just say I did it 30 times, whatever, right spot on within the margin of error of the instrument, which is like plus or minus 8 feet at that distance, right spot on for a flat Earth. I could still say, well, there might be some undiscovered fact of reality that we don't know about yet that allows that to work on a globe. See, but if I can't actually present evidence of that, then it's really not an argument, because that argument can just be used anywhere, anytime, for anything, and it's always true that there could be some unknown principle. There could be some unknown principle that hasn't been discovered yet, but that's until that gets discovered. It's no excuse to just throw out what we do know, right?
No, I'm not saying an unknown thing. Like, I was just saying leprechauns off the top of my head. But how, like in the summer, if you're out in the desert and it can be really hot, and then all of a sudden these big thunderheads will show up, and then clouds will form low in the altitude, and then they'll just almost like an atomic explosion. They'll go up into the atmosphere. All that hot air will be rising into the atmosphere, and there are other situations where cold air will actually fall down, from higher elevations for some reason. And like when you're in an airplane and you're flying, even at a high altitude, there's huge weather disturbance. Sometimes it feels like the plane is like dropping hundreds of feet at one time. I mean, it can be really scary. And those things are atmospheric conditions that are making, or atmos conditions that are making that plane go up and down or sideways or anything like that. So I think, I'm not being pedantic in that way. I mean, I've been to places where you're like on the side of a mountain, and there's huge updrafts of warm air, and birds will be flying, and they'll just be floating. They'll just be gliding, but they'll be going upward. Isn't that true?
Absolutely, but I don't see how that could explain 3,200 missing feet on a flat Earth on 29 consecutive readings.
I'm not talking about whether the Earth is flat or not. I'm just saying that, like look at the black swan. You've got this image of a pretty unrefracted looking scene, except for right around those booms. You know what I mean? Those booms are completely distorted in those picture, and I think that's because there's some kind of heat coming off that. They're doing something that's causing a lot of heat, and that's refracting, and that's completely screwing up that one little area there. That little bit of heat in that one area, just like if you had huge updrafts or disturbances in the sky that make the airplanes go up and down, anything like that.
So are you suggesting that the air currents are something that could have caused my measurements to show 3,200 missing feet?
All I'm saying is I don't know, because I don't have the data. That's a long distance. You've got, how far is it? 60 miles from your place to?
75, actually.
75 miles. Yeah, you don't know what's, like you said, we haven't been able to fly that airplane over there and see. It might be really turbulent there. There might be huge updrafts or downdrafts, or, humidity changes, or, heat being caused by something in the atmosphere. I don't know, I'm just saying that there are some other variables, and unless we did the airplane thing, we wouldn't really ever know.
Well, except we do know that on average, the density gradient does have to be bottom heavy, because if you ever have lighter weight air underneath heavy air, it's not stable. The heavy air immediately sinks and the light air rises, and it scrambles and mixes up until it's, bottom heavy again. right?
I'm not arguing that at all. No, yeah, you're right. It usually is that way. Sometimes it's not, but it usually is.
Well, it's always that way in that whenever there is lighter air under heavier air, it does correct itself somehow. It could be just wind, it could be turbulence, it could be a twister, but light air doesn't just happily stay under heavy air ever.
No, you're right, but it does happen.
Transiently. Yeah,
Right.
it happens transiently.
Everything's transient. I mean, there's constantly, variations in barometric pressure. There's weather fronts and all these things. It's in constant flux. The whole atmosphere is sometimes and sometimes there's lighter air below. Isn't that the case where, like, in valleys where you get that Thule fog? Isn't that some kind of an inversion where you have lighter air, denser air on top, or something like that?
Right, so let me explain that. That's a common misnomer, and you're definitely not the first person to misunderstand that. See, normally, as you go up in altitude, the air gets colder. Gradually, very gradually. As you go up, it gets colder, and the higher you go, the colder it gets. An inversion layer is when that gets reversed and going up gets hotter. So anytime you have cooler air below warmer air, that's an inversion layer. But it's also stable because the cooler air is down lower, and so it stays lower, and the warmer air is up higher, and so it stays higher. And yeah, it traps smoke in valleys and all kinds of stuff, but it's still a stable density gradient. It's not an inverted density, it's an inverted from the normal temperature incline. Does that make sense? It's kind of a carryover from the weatherman's world.
Yeah, I know, I can get what you're saying. So what I would say was my example, if what you're saying is true, my example of an inversion Thule fog in a valley wouldn't be a good one. But even like you were saying before I said that, is that sometimes transiently you can have a reverse where you have more dense air up higher and less dense air lower, and then it'll eventually mix itself back up and go back into its regular state. But what I'm saying is there's all kinds
Yeah.
of disturbances and variations.
It very quickly mixes itself back up. Just like the hot air balloon. Have you seen how fast a hot air balloon can rise if he feeds the fuel to it?
Hello, everybody. How you guys doing? Hello.
Really crushing it, dude.
Hey Jesse, what's up, dude?
Totally, bro.
Hey Jesse.
Yeah.
They have 4 points that have like a huge diagonal. The diagonal has, those 4 points that are very far away from each other.
Oh, the one you gave me to do, yeah.
No, the one I sent
Oh,
today.
yeah. Oh, that one. Okay.
Okay. One of those diagonals have 111 degrees. So that's too big. You won't be able to see the star in the other diagonal.
Oh.
Because the zenith angle would be 111 degrees, which means that
you have to go up in a high balloon.
yeah, yeah, the star would be 21 degrees below the horizon. I don't think that would work.
Yep, that wouldn't work. What was your question, Beryl?
I had another question about when you're in an airplane and it feels like you fall quite a few, it kind of feels like you're falling, or sometimes it feels like you're being pushed up or even sideways and stuff. What would be the atmospheric conditions contributing to something like that way up high in the atmosphere like that?
An updraft or a downdraft, or a sudden crosswind, or what they call turbulence, I guess. But that could be caused by, like, if somehow a layer of hot air gets blown underneath a layer of cold air, then it's going to create turbulence as it mixes up. Like, have you seen that experiment where you take a little food coloring and you make some blue hot water and some red cold water or whatever, and then you put the hot water on top of the cold water, and you can see how the hot water, you put the cold water on top of the hot water, and you can see how the cold water sinks underneath the hot water. I hope I got that straight. But anyway, that can create turbulence, and then there's also the trade winds, or whatever they call them, the winds that very consistently blow up at the high altitudes, which the globe model attributes to Coriolis and on the air and stuff. But anyway, those also create large rolling turbulence where they shear with lower air that's not part of the system.
So that turbulence that you feel when you're in an airplane, that would be some kind of an attempt for the pressure gradients or whatever to be stabilizing themselves. That there's an imbalance and there's like a violent reaction to that, and it's trying to get back to equilibrium again, isn't it?
It's a combination between that and, according to the globe model, the Coriolis effects on the movement of air. Yeah.
Right. Whatever you're attributing it to, it happens though. There's these really violent things that happen in the atmosphere: updrafts, downdrafts, all these winds that blow around, and all those things are showing that the atmosphere is very volatile, and that we don't really know what's between you and Mount Baker. In that, those things could be happening right there. That could be affecting it. I'm just saying, it's a possibility.
I don't see how it's a possibility. If you've got any data, I am sure glad to look into it, but the actual pressure changes are very, very small, so it's not like it's going to be causing a constant, inverted pressure gradient or anything.
I'm not saying constant. I'm saying it's ever changing. It's ever in flux, and that causes turbulence in the atmosphere.
Okay, how are you thinking this might be relevant to, like, say, my measurements?
Well, just like when you're when you're down by the water, you have this variation in, the water temperature is real cold and the air temperature is warmer. And in the atmosphere up higher, you can even have those things, because we know that, because when we're in planes, we're jostled around like that by air currents and different, updrafts and stuff like that. So what I'm saying is, if say it's this, say there was hot air trapped below cold air way up there in the atmosphere where you're flying in a jet airliner, and all of a sudden that goes to equalize itself and shift, those different temperatures are at different pressures, aren't they? Doesn't temperature cause different pressures because it makes the air expand and contract?
No, it's a fluid. It would have to be a solid in order for contraction or expansion in one area to create pressure differences.
So you're saying that gases don't expand and contract?
Oh, they do, but that doesn't change the pressure.
But there's all kinds of different pressure gradients in the atmosphere.
Well, evidently they don't vary that much, otherwise I wouldn't have gotten only 100 plus or minus 100 feet deviation over 75 miles. Right?
Well, not really, because on another day it could have been way off. It could have been way different. You're saying you did this on different day. You did that on different days, didn't you?
Oh yeah, definitely. Well, I did multiple readings on some days to see what it did throughout the day, but I did it also at all different times of year and on different years.
So you're saying that I don't understand that, like that turbulence that you feel in the atmosphere when you're in a plane, or updrafts or and downdrafts and all those kind of things, would have no effect on refraction. Is that what you're saying?
No significant effect.
Why do you say that?
You mean the significant part or the no part?
Yeah. That it wouldn't have any effect or any significant. And why would you say it was insignificant? Has it been measured?
So the pressures are measured. In fact, airplanes use altimeters that work on air pressure. So if the air pressure was changing more than just minuscule amounts, they would see it on their altimeters. And they fly all over with this. So it's not changing that much, but it's like in your, like a swimming pool or something. If you put you've seen those, like a diving depth meter. It goes on your wrist like a watch, and it tells you how deep you've dived by the pressure of the water. If you put that down, say a couple yards, it'll read 2 yards deep or whatever, and you can create currents and turbulence in your pool, but it's still going to say 2 meters deep, right? There's motion, there's minuscule pressure differences that create the swirling water and the motion and stuff, the turbulence, but the overall pressure really isn't going to change enough to be perceptible on your depth meter.
You're in the swimming pool.
Right.
But in the atmosphere, what's causing those huge, like the forces of the plane going up and down like that? What's causing that?
Turbulence in the air.
Which is what?
Which is like the equivalent of, like, let's say you drop a huge boulder in your swimming pool and it gets the water swirling and churning every which way.
Right. And what's causing that turbulence in the atmosphere?
According to the globe model, and of course I say that because I've never gone and looked, but according to the globe model, the ground is hotter around the equator because the sun puts more energy more heat into the ground. That heats the air up hotter there, and that air rises up above the equator and then flows out towards the poles where it gets cooled and sinks back down and then moves back along the ground towards the equator like this big convection thing. And then because it's moving from the equator out up high and then moving back down lower, it's changing latitude. So then that's where the Coriolis theory comes into it, to create the trade winds.
Right. Yeah, I can understand how the trade winds would be. But what I'm talking about is a very localized thing. When you're flying in a plane and, you hit this atmospheric turbulence or whatever you want to call it, updrafts, downdrafts, wind, that's a very localized thing.
Right.
What is causing it in that case? You couldn't say that the air rising at the equator was causing that little localized bit of turbulence, because you just fly in and out of it really quickly sometimes.
Well, so there's two things there. And first, I should tell you, I am not a meteorologist, so I'm kind of shooting from the hip here. If you need deeper data, you can go digging, but you're asking me, so I'm doing my best. So imagine if you have air flowing one way, and then just below it you've got air flowing the other way. Where the two streams meet, going opposite directions, there's going to be a lot of turbulence and rolling, tumbling air, So it actually just that alone could actually create turbulence. And so if you've got rolling air and the plane goes through a part that's rolling up, it's going to be lifted up. And then when it gets to the other side of the rolling air part, almost kind of like a wave. But anyway, then it's going to get pushed down. But there are also other things where just a given local region, like a city or whatever, creates a lot of heat, and the heat creates an updraft right there, which then can create its own little weather patterns.
Yeah, and that kind of goes along with what we see in the Black Swan with those little booms, huh? Some kind of heat in that area there is causing. Right, exactly. That's what I'm talking about. When you look at those booms, when you look at the booms in the Black Swan, They're really all screwed up because of refraction, and it's a very localized little thing, isn't it?
Well, in that case, it's because your line of sight to the top of the boom is not going through the same density gradient that your line of sight to the lower part of the thing is. So you're like looking through different layers from the side, and some of it gets loomed up more than others. Does that make sense?
Yeah, it's almost too. You could almost say it was a heat mirage, couldn't you?
I don't see why not. It's caused by a temperature gradient, and that's related to heat. And it's kind of like a mirage.
So a variation is in heat is causing a mirage. Now we have we don't know what the temperature gradients are or what's going on between you and Mount Baker because we can't measure it, or I guess we could if we did have a plane, we could go out and measure it. That's what I'm saying is that between you and Mount Baker in those pictures, you don't know what's going on there. That could something in the atmosphere there, updrafts, downdrafts, something being heated some way, like those booms are being heated by that source. Like you're saying, when over cities, there's big updrafts because of the heat created by the the sun hitting all the pavement down there. That's what I'm saying, is that there could be variations that are causing our vision, just like in the Black Swan, the booms in the Black Swan being distorted.
Well, the difference is we have a known, observable, repeatable phenomena relating to cold water under warm air that causes what we see close to water. So far as I've been able to find, we have no known phenomena that would cause missing height with a line of sight that was high above the water, and certainly not consistently. So I don't, if you know of some data, then I'm all ears, but I'm not aware of any.
No, I don't know any data. I haven't looked in it at all. All I know is that there are some, weird atmospheric conditions. And there might be weird atmospheric conditions between your backyard and Mount Baker.
Well, but there's none that I've heard about yet which could possibly invalidate my measurements. Does that make sense?
Yeah, but I think you're, but I'm sure you'd have to admit that there might be something there, since we do have things, like variations, like over cities, if there's some kind of heat source, like in the Black Swan thing, wind can cause turbulence, different things like that.
Well, cities, though, make things look higher. The heat from cities would make something look higher, not lower. And it's already too low, right, for the flat Earth model or paradigm. So presenting evidence that would make it, or presenting evidence of a phenomena that would make an already too low mountain look lower doesn't help the problem. Does that make sense? We need to find something. We need to find something that would cause the mountain to look lower on a flat Earth, not higher. And all the things we've discovered makes them look higher. And they still look too low, even when they're being raised up by atmospherics.
Right, but in the same vein that heat can make things look high, make things appear higher, cold could do the exact opposite if cold was dropping down.
So
if you're attributing heat to making it rise up, in the same vein, cold would make it go down, wouldn't it?
Yes, but there's one little gotcha with nature, and that is it would require the cold air to be above the hot air, and that's unstable. And the only way that can sustain itself for any length of time is if it happens right near a hot surface that's not a gas, like on a road pavement. That's how a mirage works on a road. A hot road is the road is actually hot from the sun, and it heats the air up. A thin layer of air, it heats it up. So the light actually comes down and bends away from the pavement without even hitting the pavement, because the less dense air close to the pavement. Of course, this less dense air immediately starts to rise, but the pavement is still there and it's still hot, and it immediately reheats fresh air that comes in. So it creates this continuous upside down density gradient that is less dense on the bottom and more dense on the top. But it only can happen, it can only exist for any length of time near a hot surface like that. So it doesn't happen. There's no mechanism to make it happen up high. Does that make sense?
So you're saying that there's no way that the cold air can go down below and the hot air can stay above, or vice versa?
The vice versa part, yeah. There's no, it violates the laws of density for the colder air to hover above the warmer air and just stay that way for any length of time.
Right, not for any length of time, but it is possible that that happens.
It creates tornadoes and hurricanes when it does happen.
And probably it could happen at a lesser amount than a hurricane or tornado, couldn't it? I mean, when you're in an airplane and it's being pushed down, something is pushing it down, isn't it?
Well, that would be rolling air.
But that rolling air would be rolling for some reason.
Right. It could be because of the shear between the air up above moving one way and the air below moving the other way, or it could be from like a thundercloud rising up, shooting up.
Right, so it is possible.
For brief moments.
Right. And you've got moments and moments and moments between you. You've got this 60 miles from you to Mount Baker there. And you've got moments and moments of those things can be happening. You've got this huge distance. Things could be happening like that, where air is going down, it's going up, cold air is going down temporarily and being, lifted back up, and vice versa.
Well, if I had just taken one reading, that would be a pretty good counter argument, because you could say maybe there were just conditions that just happened to be just right. But since I took 29 readings at different times of day, different times of the year, and across multiple years, that's kind of not a good counter argument, because basically we're saying that this condition would have to sustain itself all the time somehow. Does that make sense?
Yeah, but it wouldn't be like a sustained thing. It could be a thing happening, all the time, but constantly changing. You know what I mean? It wouldn't have to stay like that. It'd just be constantly changing, and that's you're getting these variations in your measurements. Don't vary by what you would call, you're saying a lot or a little, but they are varying because of different atmospheric conditions. I don't think it's the machine that's doing those variations.
Right. The machine's variation would be like plus or minus like 8 feet or something at that distance.
So those variations are, there are variations there that are causing changes.
Absolutely.
Right.
To the tune of plus or minus 100 feet at 75
right.
miles.
Right. And what we have is this idea that there's like an average, there's a formula that you guys use, or they say that there's a standard refraction. They call a standard refraction, and that's that is something that we really, how would we falsify that standard?
The best way to do that would be to create a 1 mile long, 12-inch diameter pipe with a good vacuum in it, suck all the air out, with windows on the ends, and then you could measure the path of light inside there without it being affected by refraction. That'd be a good way to do it.
Has that been done?
I'm not sure if it's been done specifically for that reason. There was a project called LIGO, which you've probably heard of by now, where it was some thing where they wanted to try to detect gravity waves from outer space, whatever. But never mind that. The point is they wanted to have a 2.5 mile long tube with a laser beam shooting right down the center of that tube and hitting a mirror and bouncing back. And they were basically building a large laser interferometer, and they were going to be running the lasers beams in a vacuum to get rid of turbulence caused by the air inside the tube. So that was these two laser beams in these two tubes. And since it was a university public funded type science research project, all the as-built blueprints are available on their website, and they show an elevation profile that shows the Earth curving 8 inches per mile squared compared to these tubes, which were allegedly straight in order to house the vacuum or the laser beam in a vacuum. Does that make sense?
Yeah, I was just talking, you brought it to this LIGO where, they set up this totally unnatural thing. Then they're using that. I mean, you're using that for some reason to say that this is the way the atmosphere would react or whatever. This is how much refraction we get because we sucked air out of a tube and shot a laser through it. And it might be true, but it's not a very natural situation like you were saying before, where if we could fly a plane and measure the measure all the things that would affect refraction along that way.
Well, the most foolproof way to quantify the effects of air on the path of light would be to measure the path of light without air, right? So that's why I brought up the LIGO thing, is because they literally were passing a laser beam through a vacuum over a long distance.
And that would give you a very consistent it would be a very consistent reading of what light was doing in a vacuum. But in an atmosphere that's constantly changing and in flux, it wouldn't be a very good comparison. That's what I'm saying. And that, like I've heard Ruhif say that he'll go up and he'll look, using a theodolite, and he'll say there's Earth curvature, and he'll even get like temperature readings, local temperature readings, and somehow calculate those in, and say, look, the Earth's a globe because I got these readings. I've used temperature. You know what I mean? He uses atmospheric pressure and all these things, and uses some kind of formula to do that. Am I right about that?
I think they basically use the temperature and the temperature gradient and the pressure to calculate the index of refraction.
So, I mean, but to do that real accurately, I think it was like what you were saying would be the most accurate way of doing it would be to actually have a plane or something fly. And even that would have its, difficulties because, like you say, I mean, the plane could fly over one area that could change in, a second. When the plane goes by, it's completely different. You know what I mean? I don't know. I'm just saying that there could be things in the atmosphere that are causing refraction or whatever.
LIGO, there's like mirrors in there or something.
Hey, Jerry, go again. You're kind of cutting out.
Did you say that in LIGO there's like mirrors or something?
Oh, I don't know if it's mirrors or prisms, but it's supposed to be some sort of laser interferometer, right? Go again?
I said,
Basically,
go ahead.
I think basically they take a laser beam, they split it in two paths, and then one path goes down one arm, hits a mirror or a retroreflector or something, comes back, and then the other half of the laser beam goes out the other arm, reflects back one way or another, and then it comes back, and then they recombine the two beams to create an interference pattern of some sort, and then they want to try to measure the effect of gravity waves that are, I don't know how it works.
Well, Jesse, it was good talking to you again. I got to take off.
It was a pleasure, sir, and thank you so much. Hit me up anytime.
All right, later.
Plum on either side.
We're not hearing you very well, Jerry.
Yeah. Can you hear me now?
We heard that.
All right. So these mirrors, are they hanging plumb?
I don't know.
Gonna have to talk to an expert about this.
Personally, I prefer using corner cube reflectors for laser interferometers because they don't have to be plumb or anything.
Well, I don't know about that. We're gonna have to get another ball expert in here.
No, these corner cube reflectors are really cool. The light comes in, bounces off 3 internal surfaces, and then shoots back out at the same angle it came in.
The same angles. So how far does that line go?
How far does what line go?
You said that it bounces at the same angle. What bounces?
The light.
Right. So how far does that go?
After it bounces?
Yeah.
Well, I guess till it hits something? I'm not sure I understand the question, or the significance of the question.
Well, you're saying that you could have a light beam go in a straight line, right? After bouncing off of one of these cube reflectors.
Well, I'm not sure what the cube reflector has to do with the light going in a straight line. It would go, in a vacuum, it would go in a straight line, essentially, into the reflector and then bounce back out and go back in the direction it came from in an equally straight
Yes.
line.
Yeah. I'm asking how far would that go? I mean, like, do you have an example of this? Like, going over a long distance?
For a retro reflector? Well, they use this for like surveyors' total stations. The one that Rakia's crew uses, or that his crew subcontracts to, is rated to bounce a light beam off of a single reflector at like 6 miles, and that's an eye-safe light source. Does that help any?
Yeah, I was more interested in the LIGO mirror thing, hanging plums.
Yeah,
But
I don't know
we're gonna
what
have
their internals are like.
yeah. All right.
My interest in it was that they drew the elevation profile in the plans to show the tube, which they claimed was straight, to be deviating from Earth's water shape level by 8 inches per mile squared.
Yeah, that's the weird part. Because if the mirrors are hanging plumb on either side, then they wouldn't meet in the middle. If the ground was a ball.
Yeah, I don't see why the mirrors would be hanging even, much less plumb. I think I think the gravity waves were supposed to actually act directly upon the 2.5 miles length of light, not the mirrors at the ends, because otherwise they could have just had, they wouldn't have had to have such long arms.
Well, Bob's here. Bob, have you taken any new pictures of the sky lately?
Yeah, as a matter of fact, I measured the orbits of 34 asteroids last night, and I may have discovered a near-Earth object.
And an orbit?
Yeah.
You said?
Yep.
Is that a straight line?
No, it's a circle or a ellipse.
But the internet says it's a geodesic.
That's under general relativity and space-time. I don't discuss space-time with flat earthers. I discuss Newtonian.
Well, it's a good thing. Who said that I'm a flat earther?
Yeah, but I don't discuss that. I discuss Newtonian physics.
Oh, I see. So Newtonian physics would say, okay, like let's say you drop something on Earth. Newtonian physics would say that it goes down in a straight line towards the center, right?
Newtonian physics says that bodies at rest stay at rest unless acted upon by an unbalanced force, and same thing for bodies in uniform motion. So if there's no force acting on it, the body won't move at all.
Well, let's say that I let go of something, right? And it falls.
Yeah. Okay,
falls
so there's
in a
force
straight
acting.
line, right?
So then there's
But
a force acting on it.
Yeah. Well, I mean, if the Earth is in orbit, then the center is moving, right? So then whatever I dropped couldn't fall in a straight line.
Depends on what frame of reference you're looking at it from.
Follow the center.
If you're in a frame of reference where
Which one is a
if you're in a frame of reference where you're following the object, it won't move at all.
Are you saying there's no way to tell?
No, I'm just saying it just depends on where you're measuring the frame of reference from.
But like,
what frame of reference are you using for dropping a ball? The frame of reference of the Earth? The surface of the Earth?
Well,
you're breaking up.
You're breaking up.
I'm trying to figure out which one would prove that it's. Oh my God! Can you hear me now?
Well, it's kind of delayed and you're a little choppy. Maybe just give it like 10 seconds. Maybe you'll come back. We heard part of it, but yeah, it was like delayed and you were breaking up.
What about now? You hear me now?
Well, let's start off with just
you're good now.
Do you agree? Do you agree that if I let go of the ball and there's no forces acting on the ball won't move?
Well, I'm not really interested in what happens. I'm interested in if it goes in a straight line. Like, I know that things fall, but the model says that like it would go in a straight line. Well, Newton said so.
No, Newton says that it will move in the direction of an applied force. It has to do with all the sum of the forces acting upon it. So if you drop the ball and there's a real high wind, it'll actually go off to the side. It'll drop down and it will also have some lateral movement to it as well. It just depends on what forces are acting on the ball.
Well, how did it form a ball in the first place?
It was made that way?
Right, by things being pulled towards the center, right?
No. A ball, if it's made out of rubber, it can be extruded into a ball-shaped mold.
No, I'm talking about what you think the Earth is. That being a big ball.
Well, you've got the force of gravity, and if the Earth is large enough, that will coalesce into a equal potential surface, and the only way to do that is to form a rough sphere. Yes.
Right. I'm saying if the center is always moving, would be, because it's going around the sun. How would it form a sphere if everything's following this moving trajectory?
You ever
Wouldn't the
hear of a
center?
Hill sphere? You
A
ever
what
hear of
sphere?
the concept of a Hill sphere?
No.
Okay. A Hill sphere has to do when you're dealing with a large object and you're dealing with other objects that are distant. If you're close to a large object, the gravity of that object tends to predominate as opposed to the gravity of a star or something. So, for example, if you're in Earth orbit, the sun doesn't really have a whole lot of effect on that because you're so close to a much more gravitationally significant mass, specifically the Earth. So whether we're in orbit, what the stars in the universe are doing really doesn't matter all that much as to whether or not a ball will, when dropped, will fall towards the center of the Earth. The forces of stars, the gravity of stars is just so insignificantly small, infinitesimally small, that it just won't have any effect compared to the force of gravity of the Earth.
Right. Well, I'm just talking about Earth and the things that were attracted towards its center, right? So this center had to have been moving, and things were attracted to it at the same time, right?
Yeah.
Right. So the only way for a sphere to form would be if the center did not move.
Well, you have to tell me, what is it moving relative to? Is it moving relative to the Earth?
It's supposed to be moving relative to the sun.
Okay, tell me how that's affecting it.
Its
Tell me how
path
that's
wouldn't be.
affecting whether or not the gravitational attraction of the Earth is pulling things towards the center of the Earth.
I'm saying that they wouldn't fall in a straight line.
Why?
Because the center's moving.
Okay, but what is the predominant factor on the surface of the Earth? How much gravitational force is acting on you if you're standing on the Earth from the sun versus the Earth?
But the center is still moving, though, right?
Relative to what? Relative to the
sun.
center of the Earth? No, it's not.
Well, why not?
Because the center of the Earth is not moving relative to the position of the center of the Earth. It's moving relative to other objects outside of the Earth, but it's not moving relative to the Earth itself.
Right. I'm saying once it got within the Earth's quote-unquote frame of reference,
yeah,
then it went towards the center, but the center was still moving. It would still have to come from outside of that frame of reference.
No, once you're within the Hill sphere, the frame of reference of Earth is the only one you need to worry about. Just like there's a Hill sphere around the moon, and there's a Hill sphere around the Earth. You know, just if you're in that Hill sphere, the main gravitational force is towards the center of the Earth. It doesn't really matter whether that center is moving relative to something else.
So once everything is inside of Earth's frame of reference, the center becomes a fixed point.
The center becomes, basically acts as a non-moving point. So when you drop a rock, it doesn't matter what the gravitational pull of the sun is on that rock. It's too small to have any effect. compared to the effect of the Earth itself. You want to try another? You want to try another game?
Well, it's not really a game, you know.
Yeah, it is. You're trying to find kinks in the system. You're trying to find something that you can hang your hat on, and it's just not working out well for you. If you
No,
want
I
to try
know.
another line of reference, you're more than welcome to.
No, I know that there's an answer for these things, but it requires you to think of in terms of frames of reference and bending straight lines and all that. I know that stuff.
Okay. Well, then you understand exactly why that is. Why the ball. Why, if you dropped a rock, it wouldn't somehow fly off the side because it's attracted to the sun.
No. I'm talking about relative to the center of the Earth.
Yeah,
Like,
it'll fall towards the center of the Earth because there's a
right.
force acting on it, forcing it to go in that direction.
Right. So there's this stuff flying around space, right? And then the center of Earth comes by. All of a sudden, this stuff.
What Earth?
What are you saying?
Are you talking about the formation of the Earth, or are you talking about
Yeah.
things like meteors? Okay,
Talking
so
about,
if you're talking about the formation of the Earth, where's the center of Earth, if it hasn't formed yet?
that's what I've been talking about this whole time.
Okay.
So for it to form a sphere, the center would have to be still.
No.
But no.
No. That's not how the Earth formed. The Earth formed from a disk of matter, and what happened was the matter started to clump together. And as it clumped together, it became more attractive to the matter around it. And that just continued until we had what is the Earth.
Come on, Jerry. You don't think that random spheres and random outer space can combine going millions of miles an hour?
They do all the time.
I don't know.
No problem.
Yeah, they do all the time.
You just clump that up a couple million miles an hour. You gotta move one like 2.4 million, one 2.3. You gotta kind of adjust it a little bit, and boom. Come on.
If they're all moving along, in a disk, a rotating disk, they're not really moving that much relative to each other.
And it's all in a flat universe, Jerry. It all makes sense. Balls are going millions of miles an hour and forming in a flat universe.
A flat universe. That's very interesting. Why would you say flat universe? You're right, by the way. But why would you say a flat universe?
In terms of that terminology, I don't say that at all. That's something that other men are claiming. Yeah.
You just said it.
Yeah, I didn't make that up though. I'm referring to the correlation of the people who claim that and put news articles and try to wrap that.
And I'm agreeing with you.
And I'm agreeing with you.
Great point that you brought up.
Currently being pushed.
Yeah, great point you brought up, and I'm agreeing with you.
Well, it's not a point, and it's nothing I disagreed or agreed with. I just said the word because they're claiming that balls formed in a flat universe going millions of miles an hour to give the perfect orchestration so that we're in the Goldilocks zone, that we can just have this flourishing, incredible, complex world of life.
Why do you think they call it the Goldilocks zone? You ever think of that?
Because it's all a fairy tale, man.
Yeah, right. No, the reason it's called a Goldilocks zone is we evolved to live here. Wouldn't it make sense that we would evolve to fit the environment that's here? If we'd evolved on Mars, we'd be living in a colder environment and breathing carbon dioxide, wouldn't we?
Well, I think
these are the conditions that we live.
They use fairy tale terminology for their fairy tale cosmology. It's perfect.
This is the environment that we were basically born to live in. This is how we developed to live in this environment. So of course this environment's correct for us. If we breathed methane, we'd be living on Jupiter. Who knows?
If we ate diamonds, we'd be living on Jupiter.
Perhaps. But we don't. We live in an environment that just so happens to be the environment where we evolved, which was Earth. Makes perfect sense. There's no way around it. That's the only reason that this is the Goldilocks zone. It's because it's the environment that we were designed to live in through evolution.
You said design, so you believe in a creator then?
Through evolution, I also said. Evolution designed us to be here. So this is our perfect environment. Makes perfect sense.
So evolution is a designer?
Evolution designs life, yes.
What designed evolution?
Maybe God. Who knows? Are you saying God couldn't design evolution?
What do you mean by God?
Well, if there's this overwhelming deity up there, could he or she have not have designed evolution to populate his realm?
I'm sure he could have.
Okay, so there you go. So evolution and believing in a deity are not mutually incompatible. A deity could have designed physics as well, could have designed gravity, because that's the way they wanted it. You know what a deity could, one thing that makes you a deity? You can't be hidden by man. So how can man hide the existence of God by hiding the flat earth? If God wished to be seen, he'd be seen. Nothing man did would change that.
Well, I think the creator can create parts of itself that can be blind from itself. It's like playing hide and seek with itself. So one could be atheist, for example. Like there could be a creator and somebody could be atheist, and that can work, meaning the creator is creating a state of atheism to experience its own divinity through. So even though it's split from itself and it's technically false and not, in the whole story, it still can create that part of itself to experience that. It's almost like that idea of playing hide and seek with yourself.
And that's fine. If that's what they want to do, they could do it, right?
Well, I think they're in a process. Yeah, I think, we all are in a relation to the whole. So,
but you know what he couldn't do? He couldn't design something like people that could hide his existence if he didn't want his existence, if he wanted his existence revealed. Kind of wrecks the entire conspiracy theory, doesn't it? Yeah, I'll let you guys think about that. I got some videos to make.
I think being able to see the Earth is what makes the conspiracy absurd.
Well, yeah, that's very true. We can see the Earth, and it's a sphere.
No, I can see it right now. Like, why should I look at internet pictures? It's like, where's the conspiracy? Like, there's the Earth right there in front of me.
Yeah, it's spherical.
well, I think the only conspiracy is that there are folks that seem to be conspiring to tell people it's a globe when it's not, but the Earth itself is just the Earth. Yeah, it's nature.
Yeah, that's what I'm saying.
Yeah, and if you look at it, it's spherical. It measures spherical. We have photographs of it being spherical. It acts like a sphere, and physics says it must be a sphere. So I'm still waiting for any evidence whatsoever, other than it looks flat to me, that the Earth is any shape other than a sphere, or technically an oblate spheroid.
What if we measured it with curved lines, but then said that curved lines are straight, and then said, well, that means that the Earth is flat because curved means straight? Would that work or no?
You mean great circles?
I mean straight curved lines at the same time.
Okay, you mean a great circle then. You understand that on different shapes, if you go along the surface of that shape, the shortest distance between 2 points is a line. And if it's a flat plane, that's a straight line. If it's a sphere, it's a great circle. What's the shortest distance between any 2 points on Earth again? Great circle?
I'm saying, well, if it's measured, why would you think that you need to call these great circles in the first place? Wouldn't you have to kind of prove that first and then say, oh, these got to be bendy straight lines?
We did.
Okay, so how did they know before they started measuring it that it was ball?
Well, they've known that from direct observations, They've known the Earth is a sphere for probably 2,300 years. The question was being able to measure how big of a sphere it was, and that took a little bit of sophisticated work by people going back to the ancient Greeks. And then they actually just went out and measured lines of latitude and longitude at different parts on the Earth.
And what was their reason for thinking that they're on a ball?
Oh, dozens. I can think of 5 right off the top of my head.
Okay, go ahead.
But why?
Well,
Go
you're
ahead
here.
and
I'm
tell
just
me how you would test to see whether or not the Earth was a sphere. What would
I
you
would-
be able to do personally to
Well,
test the shape of the Earth?
there's nothing that would give me that inclination, but it's a
Okay, well,
ball.
I'm not gonna go through them because you don't believe that your flat Earth can be falsified.
It's not flat. You can see that from the hills. But if we measured the hills with bendy straight lines, then we could just say it's flat.
Well, I'm sorry. Yeah, if you don't know what a great circle is, I can't really help you.
Yeah.
And if you want to sit down and say, well, no, the Earth isn't flat because there's hills and valleys in it, that's a little play on words, and I don't play that game.
Well, a great circle allows you to say that it's straight and curved at the same time.
What's the definition of a line?
By the
I
way,
don't
just
know.
real quick, I just wanted to say, Bob, you have straight up assumed that Jerry is quote unquote a flat earther, whatever you may or may not mean by that. And he never said those words. So just because you think what he's saying might relate to something you think is that, it's not really fair just to label and categorize him when he hasn't even said that.
Do you honestly think I haven't known Jerry for years? He's a flat earther.
We've very rarely spoken.
Whether we've spoken doesn't mean that I haven't heard you. And I've been listening to you for years. I don't always come in and speak. I wasn't speaking today until I was addressed personally. I've been here for a while, but I wasn't speaking, was I? Until I was personally addressed.
Yeah, because you post those great photos.
Well, I haven't. Yeah, I haven't done the video from last night yet. I'm a little concerned about this one that I looked at. I need to get another set of measurements on it, maybe on Sunday. Need to get a better set of measurements on it because I calculated the orbit and plotted it out, and I'm a little concerned about it.
Hey Bob, let me ask you a question. Someone told me you could prove Earth is a sphere by walking in a straight line and ending up right back where you started. Does that make sense to you, or what?
That's the concept of a great circle, yes.
So it does make sense.
Of course.
It's fascinating.
You know, you ever look at the Muslims? You ever see a Muslim mosque?
No.
There's a specific corner of a mosque called a Qibla, I believe. And
Yes.
that is the direction from the center of the room towards Mecca. That gives you a physical direction to Mecca. Do you know how they find that?
No.
Well, traditionally, now of course we have apps that do it. But traditionally what they did was they knew that on 2 days a year, at 2 times a year, because they may go over a day. But 2 times a year the sun is directly over Mecca. So if you're in the same hemisphere of the earth as Mecca, at that exact time, all you have to do is point to the sun, and that gives you the direction to Mecca. And if you're on the opposite side, the other hemisphere, relative to the hemisphere being centered on Mecca, you wait until that time the next day, and you point in the opposite direction of the shadow, and that gives you the direction to Mecca. And it's interesting because in Argentina, which is well south of the Tropic of Capricorn, do you realize that is not east, it's more south. And in New York, it's to the northwest, or the northeast, excuse me. Yet Mecca is in the Middle East. Wonder how that works out on a flat map.
Flat map.
Mm-hmm.
Aren't they all
How would
flat?
that work out on a flat Earth? It works out perfectly, of course, on a sphere, because pointing at the sun, you're pointing in the direction of a great circle to Mecca. But how would that work out? How would that work out on a flat plane?
I don't know.
Why don't you go ahead and have a look at the direction to Mecca from
Well,
areas
okay, I'm gonna look on my.
areas above the tropics?
Okay, I'll look at my compass. My compass here has two straight lines though. Is that? Are you saying that these straight lines are circles?
They're on a circle, yes.
Yeah, they say those straight lines of that compass are wrapping into spheres right before your very non-eyes.
Yep.
So then north would mean south at the same time, because I could go in the same heading. And
Well, if you headed north to the geographic north, to the North Pole, and kept going around 180 degrees, you'd end up at the South Pole. Yep.
They've warped the world in the minds of many.
Do you know compasses in the northern and southern hemisphere are built differently?
do they both utilize straight lines?
Of course.
That's interesting.
But do you know that they're built differently?
No.
Okay. You might want to look into that too. Compasses from the southern hemisphere don't work very well in the northern hemisphere, and vice versa. The reason for that is actually very interesting. I may have Wolfie send me an Australian compass sometime, and I may test it out and compare it to an American compass. See how they work. You know what would happen? Instead of being flat, the compass needle will tilt.
It would tilt relative to what?
Well, the Australian compass will tilt compared to the American compass in the northern hemisphere, and the American compass will tilt in relationship to the Australian compass in Australia. The Australian compass will be flat in Australia but tilted in North America, and the North American compass will be flat in North America but tilt in Australia.
What are the implications of this? Do you think?
Well, they have these compasses called magnetic dip compasses. They basically work vertically instead of horizontally, in a nutshell. And they claim that they pick up different vertical axes. Now, even on a globe, that wouldn't be the case, because you're still the center should always be down. So your compass, really, that the dip wouldn't exist like that. It wouldn't rise and lower. So whether it does or doesn't is an interesting quandary in and of itself. But yeah, they do have these vertical compasses, which is interesting. Be cool to play with.
You've already said why the compasses would dip, but I don't think you connected the dots as to why an Australian compass would dip in North America and vice versa. But you've already answered the question. I just don't
what
think
I'm talking about. I'm not talking about anything to do with northern and southern compasses. I'm talking about magnetic dip compasses, a specific type of compass that works on a vertical axis instead of horizontal.
Oh, that's interesting. Let's go see what you're talking about. You're calling it a magnetic dip compass.
Look up a dip compass. Yeah. It's a vertical Here, I'll post a little image of it.
Well, tell me how it works. And I'm not talking magnetic dip. You're specifically saying a vertical magnetic compass.
Yeah, it's a dip compass that measures the dip of the magnetic field.
And you say you're posting it. Let's see what you're talking about. That's not a compass, Geo. That's an analyte.
Here's another one. Dipping compass.
That's an analyte. It's not a compass. It's basically kind of like, it's the same principle as an astrolabe. Unless you're telling me that needle is magnetic, in which case you can post something about it rather than just post a picture that looks like an analyte.
Here's another one. This is a dip needle compass.
That I want to see.
Similar principle, but slightly different.
That's a picture. Let's see the write-up. Theoretically, I see what you're talking about, but all you're doing is showing me pictures of things that look like analytes. Now, what would you use that for? Geo? Could you use that to find your latitude? Going silent, huh? How would that work on a flat Earth?
Wouldn't work on flat Earth. Just change the meaning of straight to curved, or curved to straight. It's like that's the thing. It's so many people want a flat Earth model. So just
give us a model that we can test.
Yeah, just do all the bumbling bull crap that people do with geometry to make this ball model work, and you can have a flat Earth model.
Are you saying spherical geometry is wrong? Does the average sign not work or something?
I'm saying there's no way for it to be wrong, because a curved line means straight at the same time. There's nothing differentiating between what is curved and what is straight. Everything's relative.
Straight
nonsense.
is the shortest distance between 2 points on the surface of an object, be that object a plane or a sphere.
So just call the object flat.
Can you fold a sphere flat?
No, I'm saying just make any presumption you want about the surface that we're on, and just mold the geometry to fit that instead of actually using real geometry.
So you think that we just made up the idea that the Earth was spherical? You think we just made that up out of whole cloth? We have no basis for that?
Well, that's what I asked you for before, and you said that you didn't want to get into it.
Yeah, it's measured that way.
No.
100% made up.
Yeah,
okay,
it's
100% made up.
It's
someone else
with
made it up. Bob, you said we. Yeah, the person who made it up is not you. You just believe the other men that did, but it was made up. Yes.
No, I've measured it myself, so I can say without question it's spherical.
How'd you measure it? Direct measurement?
Yep.
Really?
Yep. Pretty easy to do.
Or was it derived?
Nope. Direct measurement.
From what area to what area?
Half a mile across my lake.
That's a straight line distance, or is that a great straight circle distance?
Well, it's a great circle distance, but at half a mile, there's not much of a difference, is there?
Right. You see what I'm saying?
How much drop did you measure?
2 inches.
But how could there be a drop from
2 inches of a drop in 2 miles, in a mile, half a mile?
Yeah. What's the expected
mile
drop in half a mile? What's the formula?
It's not 2 inches.
Oh, it isn't. What's the formula? Come on, you guys put it in every one of your videos. It's called 8 inches. 8 inches per mile squared, right? What would that be for half a mile?
It would have to drop from a straight line, but you already said that straight lines are circles. So this is a complete bullshit.
You're kind of fixated on straight lines and circles like you were with the 2-point thing the other day. So
well, yeah,
if it's 8 inches
you're going to
per
measure
mile
something
squared, if it's 8 inches per mile squared, what is the drop in half a mile?
Drop from what? A circle or a straight line?
Can any of you guys do that math? Come on. It's middle school.
It's all relative. Doesn't matter.
What is 8 inches per mile squared over a distance of half a mile? That's just a straight question. What is it? What would the drop be? Come on, guys. That's a 6th grade math test or math question. Somebody out there's got to be able to figure it out.
That's another thing too. You guys like to do is say, "Well, this is a 6th grade question," but I learned
it is a 6th grade question. What
but,
is 8 inches per mile squared for half a mile? It's a straightforward question. What is the answer?
But I learned that a circle wasn't a straight line like when I was like 2.
So none of you can do the math. Not one of you.
Yeah, that one comes with just a life. That comes with a basic life, Jerry.
Yeah, like there's no math if things mean their opposites.
What is 8 inches per mile squared over half a mile? How many inches is that? Come on, guys, you can do it. Or not.
If I was good at maths for you, Bob, I'd do it, but I'm not that good.
Oh, yeah, you can.
But I'm sure one of these flat earthers are better at math. Must have went to more high school level than what I did that can do math.
Yep. Yeah, Space Pope, I agree with you. Math is kryptonite to these guys. Even simple stuff like that.
Straight line seems to be kryptonite to quote unquote you guys. That's not a straight line, that's a circle. And then you want to do math on that. It's ridiculous.
Well, if you can't figure out that simple math problem, you certainly won't figure out what a great circle is and why.
There's no math to do because in math, words mean things. But in globe math, words mean their exact opposite. Whenever you want.
The drop of the Earth according to the globe model is 8 inches per mile squared. What would that be over half a mile? It's a simple question. Is it 4 inches?
Is that a 4-inch straight line or is that a 4-inch arc? Okay. Like, it's ridiculous.
Well,
Bob, I think you're trying to share your viewpoints, Bob, but you keep asking questions instead of just sharing. Why don't you just say what you want to say? Because You're getting to something about this half mile thing. What did you want to get to on it?
I want to show that you guys can do the math. So what is, if the distance is half a mile and the formula is 8 inches per mile squared, what would that work out to be? Just show me you can do the math. That's all I'm asking.
It would be 0.
Okay. Well, thanks, guys. By the way, the answer is 2 inches.
Well, did you have a point on that?
How high were you? First of all.
Yeah, I think he just did a hit and run there. That is a good point you were making earlier, Jerry, about the like on a globe, like spinning and all the different vectors, and they claim you drop something and it drops in a straight line. But then they say Coriolis bends, the path of bullets. It's all backwards.
It's a big bowl of bullshit pasta. A big jumbled mess.
Yeah, if you drop something on a globe, even if the gravity theory and the Coriolis and all of that and all the different vectors, even if that all was the case, when you drop something, it still would have a dislocation within that moving medium from straight.
What does that mean?
From straight.
From straight.
Essentially, it would be like it's chasing like a comet, right? It wouldn't fall in a straight line. It would be curved. But for it to be a ball in the first place, it would have to fall in a straight line.
Relative to
right.
What?
Relative to the center.
Why?
Because that's how the ball would form.
How high off the ground was he? Because if he's 1 feet off the ground, there is no obscurity in half a mile. Are you gonna tell me he was 0 inches off the ground or what?
Yeah, that 8 inch per mile squared thing is from the surface on a tangent at that point. That's
at a 1
just
foot observer. I mean, the 8 inches per mile square, right?
I mean, if you had drew a tangent on the ground horizontally straight out at a half a mile, there should be 2 inches of drop from it.
Hey, Gio.
Yo.
You gonna allow people to dox folks in your chat on YouTube?
I haven't been looking at the chat.
Okay, did you get my message the other day? Are you gonna let people dox people?
Definitely not.
Would you mind addressing that, please?
Who are you claiming this person is? I mean, it's not really a place for the live stream. We could talk offline, but if
I did. You didn't answer. I
would
sent you a note the other day.
What I recommend, go submit a support ticket on the server. So that would be the way to address it. It's down at the bottom. If you scroll down, it says create a ticket.
Interesting. All right. I think I'll probably just address it a different way if you're not going to have it removed.
Well, I'm suggesting you submit a ticket so we can address it. Otherwise, yeah. Thanks.
But you can't just delete it from the side chat?
Yeah, I could, but he has to let me know what he's referring to. I could go check it, though. Yeah.
Exactly. Can you go dock? I mean, blah 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 blah. Where is it at? What is it? I'm going to scroll through the whole thing. The hell? I was wondering how high was he? I mean, if he was 1 inch off the ground, then it would be 0.17 inches.
Well, if you do the mile squared, it's 1/2 times 1/2, which is a quarter, and 1/4 of 8 is 2.
Did someone ask why it's 2?
Yeah.
It's not 1/4 of 8. It's 1/4 of 0.6666.
No.
No, it'd be 1/4 of 8.
1/4 of
8 inches.
We talked about this.
You got a decimal. You just gonna put 8 on there? You just can't put 8. You gotta break it down. 8 inches is
No, it's 8 inches.
Right.
8 inches.
So what's that in decimal form?
Decimal of what?
Well, he's talking about a percentage of a foot.
Yeah, exactly.
Oh, okay. Or you could just say
you just can't put 8 inches.
8 divided by 12.
If he just put 8 inches, he just put 8. It's gonna give you an erroneous freaking an absurd number. At 1 foot is a zero obscurity. You know, you can't nothing's being obscured. Now, if you were 1 inch off the ground, then you have 0.17 inches.
0.17 inches?
Yes.
That doesn't sound right.
At half a mile.
At half a mile? No.
Yes.
Right.
I'm actually I'm in Omni Calculator. Go to Omni Calculator. You put it at every type of you can switch it to whatever measurement you need.
Uh-huh.
Right? So half a mile at 1 inch height. The distance to the horizon is at 0.35.
1 inch height.
Yeah. So there could be obscurity, yes. There could be obscurity, yes. There's enough for you can have obstruction, yes.
No, you didn't say. I didn't know it was 1 height off the surface.
Yeah. If you have it at 1 feet,
no, we were talking. That's the problem of using the drop formula to consider anything hidden. You don't use the drop formula to figure out how much is hidden. To figure out how much is hidden is a different equation, and you have to plug in your observer height and all that.
Yeah, this is the horizon, half a mile. Height level, I put it at 1 feet. This is the horizon, it's 1.225. The obscured object part will be 0 in inches.
All right, wait. So what's your horizon? 1 foot or 1 inch?
Well,
yeah,
there's
1 inch
zero. This is different. Because
there's zero hidden.
That's what I wanted to ask. How high was he? You say he measured a 2 inch drop in half a mile. So I wanted to find out how high was he, because at 1 foot you have 0 hidden.
Yeah, that's right. At a half a mile you would have 0 hidden because you could see the surface.
Exactly.
The drop is 0.14 feet in a half a mile.
Yeah, 1.2. Okay, the drop, the distance to the horizons at 1 foot observer is 1.2 miles.
Yes, horizon.
So how can you have anything hidden before that?
It's 2 inches.
It's not. The drop is not hidden.
Yeah, So you have the horizon at 1.22 miles. We all hear that over and over again, right? Now you want to know what the drop is? The drop is 2 inches, 0.17 feet.
So the drop is before the horizon?
The drop is an inch away from you.
Yeah. Think about that.
Yeah, exactly. No.
Think about that. At 1 foot observer, the distance to the horizon, that's before the drop.
The drop is where the horizon is.
Yeah, so it's the distance to the horizon is 1.2 miles.
Yes, 1.2 miles.
So how can you measure any drop before that?
Oh my!
It's a dropping the entire way. It drops. There's a 0.018 degree. You know, we always talk 0.02, 0.018 degree dip from level, and that 0.018 degree dip from level gives you a 2-inch drop over a half a mile. Why is this so hard to understand?
What's the distance to the horizon at 1 foot?
1.22 miles.
Right. So the horizon is what to y'all?
That's where things beyond it will be blocked.
Uh-huh. So if it's before that, at 1 foot, would there be a drop?
What before that?
Before the horizon.
Yeah, there's drop before the horizon, yes.
At a 1 foot observer? No, sir. You would have to be 1 inch off the ground.
No, you're 1 foot in height, and the horizon has a dip. What this says is at the horizon itself.
Where's the horizon?
1.22 miles away.
Right. So in half a mile?
It's 1.22.
Is there in half a mile?
Yes.
You still have a mile, well, 74.3 or so more miles to go before you can start seeing drop, in other words.
The ground starts falling away from your feet. It starts dropping. I mean, like an inch away. It's minuscule at an inch, but it's a constant slope away from you.
I mean, that would be the
depending on
case
your
if it was
height.
a ball.
Yeah, depending on your height is how far away the horizon will be.
Let's do it different. Let's do something different. Let's do.
How would you measure? And if you're doing an optical measurement, how would you measure something like that at a 1 foot observer? You can't. You won't be able to.
Okay.
You have to have it on the surface.
Let's do this a little differently. What do you think the drop would be if the distance of the horizon is 1.22 miles and your observer height is 1 foot? What do you think the drop is? This is a better way to look at it. This will get you straightened out. I just kind of thought about it when I heard you're kind of struggling with this, so I figured this would be the best way to
struggling.
Yeah. Tell me? What do you think the drop is if you're 1 foot observer and you're looking at a distance of 1.22?
At 1 mile, it drops 8 inches square. So it's what 0.666.
So what would it be at what would it be at 1.22 miles? The viewer height's 1 foot, and the distance is 1.22 miles. What is the drop? Give you a hint. The horizon is 1.22 miles too.
It'll be 0.99.
Oh, you put it in the calculator. Good for you.
Yeah.
12 inches.
8.25.
1 foot. So
almost,
1 foot.
Almost a foot.
Yeah. So close.
That's at 0. You know, you understand? That's like looking
That's
at
why
it.
I said this, so you can think about it for a second. So now we just changed it to 1.22 miles. I mean, it was to 1.2 miles. We changed it to observer height of 1 foot. Now we're going to change it to 0.5 feet, right? What happens then? Now the drop is 2 inches. We have to drop 2 inches. Now, nothing's hidden.
Yeah, but how did he? The thing is, he's saying, yeah, I measured it. How did he measure that?
You could do it with a theodolite. All we're seeing is wherever you are, how far that surface is lower than the surface beneath your feet.
No, the only way you can measure it is if you have obscurity.
No, that's not
You
true.
wouldn't have obscurity unless you're having a laser light going strictly around, like straight on a flat surface.
Let's do 0.25.
Well, here,
let's do a quarter mile.
let me see if I can help you out a little bit because this is all right in the video, but you
video?
can't
Give me
be
the
bothered to
video. I'll
watch
look
it.
the video.
It's right in the chat. Somebody posted.
I'll
Terry,
check
I think Terry put it in the chat. Now imagine if you would, that I have a laser 5 feet above lake level, and I shine it horizontally 90 degrees to that vertical right there. Now on the other side, I have another pole that's 6 feet tall, and that laser light hits it at 5 feet 2 inches above lake level. Do you understand how that means
I'm still
the
trying.
lake went down 2 inches?
I'm still trying to find the video.
You just got to think about it. It's not that
No,
hard.
I'm trying to find the video.
It's not difficult to do.
If you think about maybe
Gio.
if you change the distance to a quarter
Where's
mile.
the video?
Hey, think for a second before you look for your videos and go crazy. Think if you change it to a quarter mile, that drop, so the horizon is still at 1.22 miles, but what's the drop? The drop would be a half an inch. So we're talking about measuring a half an inch of drop over a quarter mile with a 1 foot observer.
Yeah, but he wasn't 1 foot. He was 5 foot, wasn't he?
Well, we're just doing 1 foot so you can look at these numbers.
It's a big difference.
It doesn't matter.
Look at Terry 33 minutes after
the
the
drop
hour.
doesn't change. The drop doesn't change at 5 feet. You're not understanding what the drop is. See, that's why I knew you were not understanding.
They're
at 5
confusing
feet,
drop with hidden. They're confusing drop with hidden.
Yeah. I figured it out, Bob. Okay, here's the problem. Look, think about it. It's not changing what your observer height. You could be 100 feet off the ground. The drop is still a half an inch for a quarter mile and 2 inches for a half a mile and 8 inches for a mile. Doesn't matter how high the observer is. Do you not get that? You thinking about it?
Might be watching the video.
You muted me?
No, he may be watching the video, which is a good thing. It's very clearly laid out in the video on how you tell the difference between a flat and a curved earth.
That's very interesting.
Was that Ebo? Who was one we were talking to? Was it Silent or Ebo? It was Ebo, right?
So what was your height above the water, above sea level?
It doesn't matter. The drop is going to be the same. It's all dependent on the distance.
Yeah, but if your drop is off, I mean,
No, the drop's not off.
how high you are off the ground.
It doesn't matter.
Yes,
the drop
it
is still the
does.
same.
Yes, it
No,
does.
the drop is exact. No, listen to me.
No, because
listen
if
to
you
me. Listen to me. Listen to me.
up.
The drop
No,
is
I'm not
8 inches
listening.
per
I'm
mile.
listen to me.
It doesn't matter how high you are. That's what you're
I don't
making
care
a
about
mistake.
what I don't care about what you're talking about the drop. I'm talking about what he's saying in his video, dude.
It's very clear. Numbers are all right in the video too. Has nothing to do with the horizon or hidden heights or anything. It is strict. When you're standing on top of a ball, you realize the ball's surface drops away from you in all directions, right?
The water surface. You're measuring some elevation on the land with the elevation you have in your area, and you're trying to say you measured the surface of the water. You didn't measure the surface of the water.
I most certainly did.
Oh, sure you did.
Yeah, it's right in the video.
Why are you
Absolutely
fighting
measured it. I did it in reference to the surface of the lake.
Oh, you've referenced it. Okay.
Yeah, I measured it directly to the surface of the lake. All my marks were based on elevation above lake level.
The interesting thing about this is you can get so high up above the
Pure
surface you don't have this.
bro.
Hey, listen, you can get so high above the surface that you don't have a refractive issue. That's one thing nice about this. All you know is a distance. If you know distance to the point, you know what the drop's going to be. And that drop tells you the curvature.
Well, I know that on a flat, if the earth was flat, the elevations above lake level would be exactly the same on both sides of the lake. However, they're not. That's the problem.
I.e., there'll be no drop.
Yeah, there's no drop because
No
it's
drop.
a flat surface.
Your elevation.
However, there is
What's
a
your
drop.
elevation?
Doesn't matter.
Yes,
That's
it
irrelevant.
does. Wow.
You keep on saying it does, but it doesn't. We're trying to help you understand. You're
All right,
fighting us like a flat.
I did the test. Go ahead and ask me.
Yeah. Why does the drop matter to you?
No, I'm asking what was the elevation of its elevation.
And I will tell you under one circumstance, and that is you tell me why it makes a difference.
What was the elevation of the apparatus?
Tell me why you feel that's important.
Dude, if you're not gonna answer the question, I'm not gonna whatever.
Because you don't understand, do you?
Yeah, you don't understand.
No, I do understand.
Yeah, he doesn't have the first clue. I'll
I would
answer
say
your question if you'll tell me why you think it makes a difference.
It's a fair question, Evo.
Yep. Just tell me why you think it makes a difference, and I'll answer.
Hello? Elbow.
I wonder if he thinks the extra 8 feet in radius of the Earth is going to make a difference in the curvature drop.
I know, right?
It technically will, but I think he'd be pretty hard pressed to measure it.
Yeah, that would be such a talk about rounding errors. I guess this is like
Yep. Number of significant digits would be a little tough on that one.
Mm-hmm.
Not to mention the fact that the 8 inches per mile square is an approximation to begin with.
Correct. It's not even really that accurate because it's not really the equation for a
No, it's not. No, it's not, but it works well enough for half a mile.
Oh yeah, of course. But this, I think we may be making headway here because once he realizes that it doesn't matter what the observer height is, then you start understanding what drop really means. And when you start looking at things that are below level, then you start realizing, that's the drop. That indicates that something either is going wrong here. We have a curved surface, or there's some kind of refraction, or someone's playing tricks on me, or my measuring equipment's wrong. I mean, you got to really start doing some soul searching when you have a value like that.
Yep. And I did put in quite a bit of margin of error on that too. It had to be more than 1.5 inches to be considered real.
What if we can? We've always talked about taking multiple measurements higher and higher and higher, and then giving the differential value for the refraction based on the distance. But could there be a way we could test some area above the surfaces where there is the lowest refraction possible, and we can measure there's no refraction? Some kind of test for that.
Well, I actually thought about putting up a refraction meter in the backyard. If you set the crosshairs on a point on the other side of the lake, and you went out and just consistently measured the water temperature and measured the air temperature, and saw where the crosshairs hit on the scale on the other side, you could actually directly calculate refraction that way and compare it to temperature of water and temperature of air.
Right.
That would be kind of a neat. That may be a little trick I'll do during the summer when we get cooler water and warmer air.
Right.
I may do that for a week or so just to kind of measure it and see what happens.
Then we can start getting a more solid answer for drop under all conditions, and then take.
They're having too much trouble with the concept of drop versus hidden height.
I know, right?
It's kind of funny.
Oh boy! Oh boy!
The fact they couldn't do that simple math problem kind of blows my mind.
but they're so confident.
Yeah.
Then you're gonna anyway. They're calling you a sophist. You're using sophistry, Bob. You're just trying to confuse
Well, I
them
have
with
a
your
sofa
weight.
in the living room. Does that count?
Well, of course it does. That's obvious. Now we know. Now we have the answer we're looking for.
Yep.
Bob has a sofa in his house. No wonder.
Yeah. I went out and hit 34 asteroids last night, man.
No kidding.
And I think I may have discovered a Neo for 35. I need further observations because I'm a little bit worried about the orbit that I calculated for it.
Worried for us or worried about that you're wrong?
Worried for us.
Oh, shit.
Yeah, it crosses the Earth's orbit twice. Twice.
Sounds like you might want to report that.
I did. But more importantly, I've got to get better measurements. I'm hoping Sunday night I can get it, and I want to get a good hour and a half's worth of measurements on it, and see if I can characterize that orbit a little bit better.
How much time do we got?
I don't know.
I gotta know whether it's time. If it's 1999.
You don't look
Well,
up.
the thing about it is it crosses the path of the Earth's orbit twice, and whether or not the Earth happens to be in that exact spot, I don't know. I don't know when that'll happen. But it was a concerning enough thing that I did report it, and I am going to be following up on it, and so are other people. I've got some other people looking at it too. I've got the orbital elements for it, and you can get the ephemeris from the orbital elements, and they're going to actually look at it. I hit it with the RASA and the 6200.
Mm-hmm.
It's a magnitude.
You got some kind of angular change to get a approximation on the velocities, or how do you, or is it already registered?
No, what you do is you take 60 images, 60 1-minute images,
right,
and you watch it move in relationship to the background stars.
Okay.
And you calculate its position at each of those 60. Say you get 20 observations that contain that one. You calculate its exact position angularly from comparing it to the stars in the background at each of those positions, and then you see how fast it's moving. Main belt asteroids, their velocity is generally 1 arcsecond a minute, I believe it is. And near Earth objects are greater than 1.5 arcseconds per minute because they're moving faster because they're closer to us.
Right. So you can verify that it's in the asteroid belt rather than.
I can see if it's a main belt or whether or not it's a crosser. This son of a bitch is moving at 2.62, so it's close, and it's a magnitude 18.5 asteroid, so it's pretty dim. I was very lucky to pick it up, but now that I know right where to look for it, I should be able to see it on Sunday.
Yeah. Well, yeah. Let us know again when you get up there and capture it.
Well, I compared it to I ran it through the databases, and there's no asteroid there. There's no reported asteroid there.
Right.
Yet there it is.
Well, on Sunday I'll be waiting to see what you come back with. It wasn't there. It was a satellite.
Well, I'm hoping it's going to be an error. If you don't hear anything, it might not have been an error.
Okay. Hope it was an error.
Are you going to be Bob the Nobel Prize guy for saving the Earth?
No, I prefer I prefer Bob the benefactor and savior of the Earth.
How about Bob the pseudo guy?
How about you kiss my ass?
Bob will be bigger than Jesus. You guys will have statues made after him.
I don't know if they'll have time. Carving my nose may take too long. I don't know. We'll see.
I understood that nose one. What are you saying? That you're a Jew?
No, I just have a big nose.
So yes, just kidding.
Hey, I got Corsican in me. What can I say?
Let's just say he likes kosher meat, right?
You know, it's amazing what a guy with a telescope in his backyard can do.
Hallmark of science. Get your ass out.
You know, this is citizen science at its best. Most asteroids are found by people like me. They have sky surveys. They have governmental sky surveys. Atlas is one of them. But their equipment is really not that much different than what I'm using. Except they've got 4 of them. I just have 1. They use quad mount RASs. So I've got the one telescope. They've got a mount that's got 4 of them on it in an array.
Satellites and probes ever get just completely obliterated by some rogue asteroid?
Well, yeah, we hit one. Yeah, we hit one not long ago. That thing was close enough. I probably could have seen it if I'd had the weather for it. I tried to get Artemis, but I never got. I mean, I had solid clouds for a month. A couple of the guys, our Astronomy Live got Artemis on the way back. That's one of the ways we know it was real. We actually had people that saw it. Yeah, man, I had an angel donor bought me a state-of-the-art astro camera, and the first, I tested it on nebula and stuff, and then last night I decided I was going to test it out on asteroids, even though it was a color camera. And the first track was this fucking Rogue, this Neo. I think I'll name it after my wife if it's real.
Always a pleasure, huh?
At least Bob actually comes in here and talks. A lot of guys like to just sit in the chat all day and break balls. do you think that you run